Good evening, and welcome to The Sleepy Scientist. It really is brilliant to have you here. Tonight we're exploring something so familiar that it's easy to forget how strange it truly is: matter. Before we settle in, one small favour. When a quiet moment allows, do wander over to our ebook on the Sleepy Scientist website. It gathers the ideas from these videos onto the page and lets them unfold slowly, with all the room they need to make proper sense. The whole thing is narrated as well, so you can read it, or simply close your eyes and listen. And at the end of each movement there's a short quiz waiting, a gentle way to see what's taken root before you move on. You'll find a QR code on screen for the first 5 minutes or so, no rush at all, and a link in the description across to the sleepyscientist.com that stays put for whenever you're ready. Every reader who takes a look is quietly keeping these videos going, and to anyone who buys a copy, I don't think you know how much that means. That's the only ask tonight, and thank you, sincerely. Now, wherever you're listening from, take a moment to get comfortable, settle in, and let us slowly explore how matter actually works. Everything around you, from the air in the room to the surface beneath you, is made from it. And yet, when we look closely enough, solid objects stop appearing quite so solid, atoms turn out to be mostly open space, and the simple idea of matter begins to unfold into particles, forces, fields, and quantum behaviour. So, get comfortable, settle in, and let's begin. Matter is so familiar that it rarely seems mysterious. It is the air filling the room, the water in a glass, the stone beneath a path, the grain of wood in a table, the cool surface of metal, the softness of skin, the transparency of glass, and the ground holding everything steadily in place. These materials feel simple because we encounter them constantly. They appear solid, continuous, and dependable. Yet beneath that calm surface, each one is built from several layers of physical organisation, with structures nested inside structures, and rules operating across scales too small to see directly. In practical terms, matter can be described as physical systems made from particles and fields that possess measurable properties such as energy, momentum, mass, electric charge, and angular momentum. This definition is useful, but it immediately carries us beyond the old picture of matter as nothing more than tiny solid pieces. Modern physics does not describe the universe as a collection of miniature pebbles moving through completely empty space. Instead, matter is understood through quantum states, interacting fields, particles that display wave-like behaviour, and collective patterns that appear only when enormous numbers of components act together. Matter and energy are also not simple opposites. Matter carries energy in many forms. It can possess energy because it is moving, because it is hot, because its atoms are chemically bonded, because its particles are electrically arranged, or simply because it has mass. Albert Einstein's special theory of relativity revealed that mass itself contributes to the energy of a physical system. The familiar relationship is written in words as energy equals mass multiplied by the speed of light multiplied by the speed of light. This does not mean that matter and energy are identical labels for exactly the same thing. Matter refers to particular physical systems and forms of organisation, while energy is a measurable property that can be transferred and transformed. A stone is matter. The energy stored in its mass, temperature, chemical structure, and motion describes aspects of that stone. The deeper puzzle is how such a limited collection of underlying ingredients produces the extraordinary range of properties found in the world. Matter can be solid enough to support a building or fluid enough to pour through a narrow opening. It can be gaseous, rigid, flexible, transparent, opaque, hot, cold, magnetic, electrically charged, chemically reactive, or almost completely inert. It can form a crystal, a cloud, a flame, a living cell, or a human brain. These properties are not simply hidden inside individual atoms in miniature form. A single iron atom is not a tiny hard grey fragment of metal. A lone water molecule is not wet. One carbon atom is neither a diamond nor a piece of graphite. The familiar properties of materials emerge when vast numbers of particles interact. Wetness appears when many water molecules move together and interact with a surface. The strength of steel depends on how enormous numbers of iron atoms are arranged, how their electrons behave, and what impurities or defects are present. The flexibility of skin depends on molecules such as collagen, elastin, water, fats, and proteins forming organized biological structures. Color depends on the way electrons within matter absorb, reflect, transmit, or scatter different frequencies of electromagnetic radiation. Temperature reflects the statistical distribution of microscopic energy among countless particles. The large-scale behavior is real, but it belongs to the organized system rather than to any one isolated ingredient. To understand matter, it helps to move gradually through its different levels. At the largest scale are familiar objects made from particular materials. Materials may contain mixtures of substances or repeated structures built from molecules. Molecules are arrangements of atoms held together primarily by electromagnetic interactions. Atoms contain electrons surrounding compact atomic nuclei. Those nuclei contain protons and neutrons. Protons and neutrons are themselves composite objects made from quarks and gluons. Electrons, as far as current experiments can determine, are elementary particles without known internal parts. At a still deeper descriptive level, modern quantum field theory treats particles as excitations of quantum fields. An electron is an excitation of the electron field. A photon is an excitation of the electromagnetic field. Quarks and gluons are excitations of their corresponding fields. These fields interact according to fundamental physical laws, producing the particles, forces, bonds, reactions, and structures from which ordinary matter emerges. This scientific picture is remarkably successful. It explains atomic spectra, chemical bonding, electricity, magnetism, the strength of materials, nuclear reactions, and the behavior of subatomic particles with extraordinary precision. Yet it is not a finished account of everything. Quantum field theory describes 3 of the known fundamental interactions extremely well, but gravity is still described separately by Albert Einstein's general theory of relativity. Physicists do not yet have a complete experimentally confirmed theory uniting gravity with quantum mechanics. Dark matter presents another major uncertainty. Astronomical observations show that galaxies and galaxy clusters behave as though they contain far more gravitating matter than can be seen through ordinary light. Whatever dark matter is, it does not appear to be made from the same ordinary atomic material that forms stars, planets, and people. The earliest universe also remains partly hidden from us, especially at energies where current theories may require a deeper framework. Even the apparent solidity of the room is subtler than it seems. When a hand rests on a table, the atoms in the hand do not meet the atoms in the table as perfectly hard balls striking one another. Atoms have no sharp outer shell. Instead, the electron distributions of the 2 materials interact through the electromagnetic force. As the atoms are pushed closer together, their negatively charged electrons strongly resist being compressed into the same region. The Pauli exclusion principle also plays a central role. This quantum rule states that identical particles known as fermions, including electrons, cannot occupy the same complete quantum state. Together, electromagnetic repulsion, available quantum states, and the Pauli exclusion principle create a powerful resistance to compression. The table feels solid because its internal quantum structure prevents the matter in your hand from simply passing through it. So the world around us is solid without being made from perfectly solid little pieces. It is stable without being motionless. It is familiar without being simple. Matter works through layers of organization, from everyday objects to atoms, nuclei, particles, interactions, and quantum fields. What seems like an ordinary surface is the visible result of an immense and almost unimaginably intricate physical arrangement, quietly maintaining itself beneath every touch. Long before anyone could see an atom, people were already trying to understand what the world was made from. The earliest explanations were not based on microscopes, particle accelerators, or carefully controlled chemical experiments. They came from direct experience. Earth seemed solid and heavy. Water flowed and changed shape. Air moved invisibly around the body. Fire transformed whatever it touched. Together these became the classical elements of earth, water, air, and fire. This system was not a microscopic theory in the modern scientific sense. It did not describe hidden particles or explain matter through measurable internal structure. Instead, it organized the visible qualities of the world. Dryness, wetness, warmth, coldness, heaviness, lightness, movement, and transformation could all be discussed through combinations of the four elements. The model was simple, memorable, and flexible enough to survive for centuries, which is often the fate of an idea that is useful before it is accurate. Some ancient Greek thinkers imagined a very different possibility. Leucippus and his student Democritus proposed that matter might be made from tiny indivisible units moving through empty space. Democritus called these units atoms, from a Greek word meaning uncuttable. In this picture, visible change did not require matter itself to appear from nothing or vanish completely. Instead, atoms could separate, combine, and rearrange. Democritus imagined atoms differing in shape, size, and arrangement. Smooth atoms might produce one kind of substance, while rough or hooked atoms might form another. None of this was established experimentally. Ancient atomism was a philosophical proposal, created through reasoning rather than measurement. Democritus did not know about electrons, atomic nuclei, chemical elements, or quantum mechanics. Still, the central idea was striking. Perhaps the continuous world of experience was built from discrete units too small to see. Atomism was not the only view available. Aristotle argued that matter was continuous and could, at least in principle, be divided without reaching a final indivisible piece. He developed a highly influential system based on matter, form, qualities, and the four classical elements. Because Aristotle's work became deeply embedded in European and Middle Eastern scholarship, his continuous picture of matter remained dominant for many centuries. There was no decisive experiment capable of settling the dispute. An ancient observer could crush a stone into smaller fragments, grind those fragments into powder, and still see no obvious final unit. Water appeared smooth and continuous. Air filled every available space without revealing separate pieces. Both atomism and continuity could be made to fit ordinary experience. Without precise measurements, they remained competing ways of thinking rather than testable physical theories. The discussion began to change as experimental chemistry developed. During the 17th century, Robert Boyle challenged traditional ideas about the elements. In his work, The Skeptical Chymist, published in 1661, Boyle argued that substances should be investigated through experiment rather than accepted through inherited philosophical categories. He distinguished chemical elements from compounds more clearly and treated elements as substances that could not be broken down into simpler materials by known chemical methods. Boyle did not possess the modern periodic table, and his definition was not identical to the one used today. Even so, his approach moved the study of matter toward repeatable experiments, careful observation, and chemical analysis. During the late 18th century, Antoine Lavoisier brought even greater precision to chemistry. He measured the masses of substances before and after reactions and helped establish the law of conservation of mass. In ordinary chemical reactions conducted within a closed system, the total measured mass remains essentially constant. Materials may burn, dissolve, release gases, or form new compounds, but matter is rearranged rather than simply destroyed. Lavoisier also helped replace older theories of combustion with an account involving oxygen. His work demonstrated that careful weighing could reveal patterns hidden beneath dramatic visible changes. A flame might look mysterious, but a balance could make it answer questions. Joseph Proust then established the law of definite proportions. A pure chemical compound always contains the same elements combined in the same proportions by mass. Water, for example, does not contain arbitrary amounts of hydrogen and oxygen. Its composition follows a fixed relationship. This regularity suggested that compounds were not continuous mixtures assembled in any imaginable ratio. Something discrete seemed to be controlling the combinations. John Dalton used these chemical patterns to formulate an atomic theory in the early 19th century. Dalton proposed that each chemical element consisted of its own type of atom, that atoms of different elements differed in mass, and that compounds formed when atoms combined in simple whole number ratios. Chemical reactions, in his model, rearranged atoms without creating or destroying them. The theory explained why elements combined in fixed proportions. If matter were made from discrete atoms, then a compound might contain one atom of one element for every one or two atoms of another. Half an atom could not casually wander into the arrangement. Chemistry's neat numerical ratios began to make sense. Dalton's atoms were very different from the atoms understood today. He treated them as solid and indivisible units. He knew nothing of electrons, protons, neutrons, nuclei, orbitals, or quantum fields. Some of his proposed atomic masses and molecular formulas were incorrect. Yet his theory transformed atomism from an ancient philosophical idea into a scientific model tied directly to experimental measurements. Another major pattern emerged through the work of Dmitri Mendeleev. In 1869, Mendeleev arranged the known chemical elements into a table based largely on atomic mass and recurring chemical properties. Elements with similar behavior appeared at regular intervals. More impressively, Mendeleev left gaps where the pattern suggested that undiscovered elements should exist. He predicted properties of several missing elements, including substances later identified as gallium, scandium, and germanium. When these elements were discovered and broadly matched his predictions, the periodic table became powerful evidence that matter possessed a hidden order. Mendeleev did not know the modern explanation involving atomic number and electron structure, but the repeating pattern was already visible. At the same time, physicists were using atoms and molecules to explain gases and heat. James Clerk Maxwell developed a statistical description of molecular speeds and gases. Ludwig Boltzmann extended this work and connected microscopic motion with temperature, pressure, and entropy. In kinetic theory, gas pressure arises because countless particles collide with the walls of a container and transfer momentum. Temperature reflects the statistical distribution of microscopic energy among those particles. A gas that appears calm and still on a human scale can contain molecules moving rapidly in every direction. The stillness belongs to the average, not to the individual particles. Many scientists remained cautious about whether atoms were real physical objects or merely useful calculating devices. One of the strongest pieces of evidence came from Brownian motion, the irregular movement of tiny particles suspended in a liquid. In 1905, Albert Einstein explained this motion as the result of countless uneven collisions with invisible molecules in the surrounding fluid. Although the suspended particle is struck from every direction, the impacts never balance perfectly at every instant. It therefore jitters unpredictably. The French physicist Jean Perrin later performed detailed experiments that supported Einstein's analysis. His measurements allowed atomic quantities to be estimated and helped persuade the scientific community that molecules and atoms were genuine physical entities. By the beginning of the 20th century, the atomic picture had succeeded because it connected hidden structure with visible measurements. Fixed chemical ratios, gas pressure, temperature, diffusion, Brownian motion, and the periodic table could all be understood as consequences of microscopic particles and their arrangements. Atoms were no longer merely imagined pieces of matter. They had become the unseen explanation behind a growing network of experiments. The world still looked continuous to the eye, but its behavior increasingly revealed a deeper, discrete organization beneath the surface. By the end of the 19th century, atoms had become essential to chemistry and physics, but they were still often imagined as indivisible units. John Dalton's atoms could combine and rearrange, yet they contained no known internal parts. That picture began to change through experiments involving electricity, gases, and glass tubes, from which much of the air had been removed. When a high voltage was applied across electrodes inside one of these tubes, a strange glow appeared. Rays seemed to travel from the negatively charged electrode, known as the cathode, toward the opposite end of the tube. These became known as cathode rays. Scientists, including William Crookes, investigated how the rays moved, how they cast shadows, and how they could produce fluorescence when they struck certain materials. The nature of cathode rays was uncertain. Some researchers thought they might be a form of electromagnetic radiation. Others suspected that they were streams of charged matter. The answer would reveal that atoms were not nearly as indivisible as they had seemed. At the Cavendish Laboratory in Cambridge, J.J. Thomson studied how cathode rays responded to electric and magnetic fields. Because the rays bent toward a positively charged plate, Thomson concluded that they carried negative electric charge. By measuring the amount of deflection, he estimated the relationship between the charge of the particles and their mass. In 1897, Thomson announced that cathode rays consisted of negatively charged particles far lighter than any known atom. Their charge-to-mass ratio was enormous compared with that of charged atoms, implying either that they carried an unusually large charge or that their mass was extraordinarily small. Further evidence showed that the mass was indeed tiny, roughly 1/1800th of the mass of a hydrogen atom. These particles later became known as electrons. More importantly, they appeared regardless of which gas filled the tube or which metal formed the electrodes. Electrons therefore seemed to be universal components of matter rather than fragments belonging to one particular element. The atom had been opened. This discovery created an immediate problem. Ordinary atoms are usually electrically neutral. If they contain negatively charged electrons, they must also contain positive charge somewhere within them. Thomson proposed one of the first internal models of the atom to account for this balance. In Thomson's model, the atom consisted of a diffuse sphere of positive charge with negatively charged electrons embedded throughout it. The model later became known as the plum pudding model, although the culinary comparison depends somewhat on which pudding one has in mind. The electrons played the role of small pieces distributed inside a larger positive substance. The model was eventually shown to be wrong, but it was not unreasonable. It incorporated the newly discovered electron, preserved the atom's overall electrical neutrality, and avoided placing large amounts of like positive charge in one tiny region. What it lacked was direct evidence about how the positive charge and most of the atomic mass were actually arranged. That evidence came from experiments led by Ernest Rutherford at the University of Manchester. Rutherford had previously studied radioactivity and identified alpha particles as positively charged particles emitted by certain unstable materials. He asked Hans Geiger and Ernest Marsden to investigate how alpha particles were scattered when they passed through very thin sheets of metal. The most famous version used a sheet of gold only a few hundred atoms thick. Alpha particles were directed toward the foil, and flashes of light on a surrounding detector revealed where they travelled after passing through it. If Thomson's diffuse model were correct, the alpha particles should experience only gentle forces spread across the atom. Most were expected to continue almost straight ahead, perhaps with slight deflections. Most did exactly that. The surprising result came from the small minority that did not. Some alpha particles were deflected through large angles. A very small number even rebounded in roughly the direction from which they had arrived. Rutherford later compared the surprise to firing a projectile at tissue paper and having it return toward the source. The result suggested that the atom's positive charge and most of its mass were not spread smoothly throughout its volume. They were concentrated in a region so small that most alpha particles missed it completely, while the rare particle passing close to it experienced a powerful electrical repulsion. In 1911, Rutherford proposed the nuclear model of the atom. At its centre was a tiny, positively charged nucleus containing almost all of the atom's mass. Electrons occupied the much larger region around it. This was a radical rearrangement of the atomic picture. Nearly the entire atom appeared to consist of the space between a minute nucleus and the outer electron distribution. The scale difference is difficult to picture. A typical atom is around 1/10 billionth of a metre across. Its nucleus is tens of thousands of times smaller in diameter. If an atom were enlarged until it spanned a large stadium, the nucleus might be roughly comparable to a small object near the centre, while the electron region extended throughout the stadium. This is why atoms are often described as mostly empty space. The phrase is helpful, but only up to a point. The atomic region is not a miniature room containing a hard nucleus and a few tiny balls flying through literal nothingness. Electromagnetic fields extend through the atom, and quantum mechanics describes electrons through probability distributions that occupy the surrounding region. The space is not filled with ordinary solid material, but neither is it physically meaningless. Rutherford's model also raised a new question. What determined the identity of an element? Chemists had often arranged elements according to atomic mass, but this produced irregularities in the periodic table. The English physicist Henry Moseley provided a clearer answer through experiments with characteristic X-rays. When different elements were bombarded with energetic electrons, they emitted X-rays with frequencies that followed a systematic pattern. Moseley showed that this pattern depended on the positive charge of the nucleus. This nuclear charge corresponded to a whole number, now called the atomic number. Hydrogen has atomic number 1 because its nucleus contains 1 proton. Helium has atomic number 2 because it contains 2 protons. Carbon has 6, oxygen has 8, and gold has 79. The number of protons, not the total atomic mass, defines which chemical element an atom belongs to. Yet another difficulty remained. Measurements of nuclei suggested that they often possessed more mass than their positive charge alone could explain. For example, a helium nucleus had twice the positive charge of a hydrogen nucleus, but roughly 4 times its mass. Some additional electrically neutral components seemed to be present. In 1932, James Chadwick discovered the neutron. By studying penetrating radiation produced when beryllium was struck by alpha particles, Chadwick showed that the radiation consisted of electrically neutral particles with masses close to that of the proton. Neutrons resolved several puzzles at once. They contributed nuclear mass without increasing electric charge, and they explained isotopes. Isotopes are atoms of the same element with the same number of protons but different numbers of neutrons. Carbon-12 and carbon-14 are both carbon, because each has 6 protons, although carbon-14 contains 2 additional neutrons and is radioactive. The basic atomic inventory was now becoming clear. Electrons carry negative charge and occupy quantum states around the nucleus. Protons carry positive charge and determine the chemical identity of the element. Neutrons carry no net electric charge and contribute to nuclear mass and stability. Protons and neutrons are each nearly 2,000 times more massive than an electron, so almost all ordinary atomic mass is concentrated in the nucleus. It is tempting to picture this arrangement as a miniature solar system, with electrons circling the nucleus like planets around the sun. That image captures the enormous difference between the size of the nucleus and the size of the atom. But it fails as a physical description. Charged electrons moving in classical orbits should continuously lose energy and collapse into the nucleus. Real atoms do not behave that way. The discovery of the atom's interior therefore solved one mystery while creating another. Matter contained electrons, protons, and neutrons, arranged across an immense difference in scale. But explaining how those particles form stable atoms would require abandoning ordinary mechanical orbits and replacing them with the stranger, more accurate language of quantum physics. Rutherford's nuclear atom was a remarkable improvement over the earlier picture of positive charge spread throughout the atom. It placed nearly all the mass in a tiny central nucleus and left the electrons in the much larger region surrounding it. At first glance, the arrangement looked reassuringly familiar. The nucleus resembled the Sun, while the electrons appeared to circle it like planets. The difficulty was that electrons are not planets. An electron carries electric charge, and a charged particle moving in a curved path is accelerating, even if its speed remains constant. According to classical electromagnetism, an accelerating charge should emit electromagnetic radiation. That radiation carries energy away. A classical electron orbiting a nucleus should therefore lose energy continuously. Its orbit should shrink, its motion should change, and it should spiral rapidly into the nucleus. Calculations suggested that an atom built this way would collapse in a tiny fraction of a second. Ordinary matter clearly does not behave like that. Tables do not suddenly lose their electrons before breakfast, and the atoms in the air have survived rather longer than classical theory allowed. Something fundamental was missing. Another problem came from the light emitted by atoms. When a hot solid glows, it can produce a broad range of wavelengths. But isolated atoms in a gas emit light only at particular frequencies. When this light is separated into a spectrum, it appears as distinct lines rather than a continuous rainbow. Hydrogen produces a characteristic series of spectral lines. Classical physics could not explain why the atom selected these exact frequencies. If an electron could orbit at any distance and possess any energy, the light it emitted should not be restricted to such precise values. The first major clue arrived from a different problem involving blackbody radiation. A blackbody is an idealized object that absorbs all electromagnetic radiation falling upon it and emits radiation with a spectrum determined by its temperature. Real objects can approximate this behavior well enough for the pattern to be measured. Classical theories predicted far too much radiation at short wavelengths. This failure became known as the ultraviolet catastrophe. The theory suggested that a heated object should release an unlimited amount of energy in the ultraviolet region, which was not merely inaccurate but energetically rather ambitious. In 1900, Max Planck found a mathematical solution. He proposed that matter exchanged electromagnetic energy in discrete amounts, rather than in an endlessly divisible flow. These packets depended on the frequency of the radiation. The relationship can be stated as the energy of one quantum equals Planck's constant multiplied by the frequency. Planck initially treated quantization as a way of solving the radiation problem rather than as a complete revolution in the nature of energy. Yet the idea introduced something new. At microscopic scales, certain physical changes might occur only in permitted amounts. Albert Einstein took this possibility further in 1905 while explaining the photoelectric effect. In this effect, light shining on a metal surface can eject electrons from it. Classical wave theory suggested that sufficiently intense light should eventually free electrons regardless of frequency, because a stronger wave should deliver more energy. Experiments showed otherwise. Below a particular threshold frequency, electrons were not emitted even when the light was intense. Above that threshold, electrons could be released almost immediately. Increasing the light's intensity increased the number of emitted electrons, but their individual maximum energies depended primarily on the light's frequency. Einstein proposed that light transfers energy in localized packets. Each packet carried an amount of energy determined by its frequency. These packets were later called photons. One photon could transfer its energy to one electron. If the photon did not carry enough energy to overcome the binding of the electron within the material, increasing the number of equally weak photons did not solve the problem for an individual interaction. More photons could knock out more electrons, but only when each photon carried sufficient energy. The idea of quantization was no longer confined to radiation emitted by hot objects. It was beginning to reshape the understanding of light itself. In 1913, Niels Bohr applied quantization to Rutherford's atom. Bohr proposed that an electron in hydrogen could occupy only certain permitted orbits, each associated with a specific energy. While occupying one of these allowed states, the electron would not radiate energy continuously. Light would be emitted or absorbed only when the electron changed from one permitted energy level to another. the photon's energy would equal the difference between those two levels. A transition involving a larger energy difference would produce higher frequency radiation, while a smaller difference would produce lower frequency radiation. This explained why hydrogen emitted discrete spectral lines. The atom did not offer an unlimited range of energies. It possessed a particular ladder of allowed values, and its light revealed the gaps between them. The Bohr model successfully reproduced the main structure of the hydrogen spectrum and calculated the size and energy of the hydrogen atom with impressive accuracy. It gave physicists a workable picture of atomic stability and quantist energy. However, it remained a hybrid model. It combined classical circular orbits with new quantum rules imposed from outside. It did not explain why only certain orbits were permitted, and it struggled with atoms containing more than one electron. Fine details in atomic spectra, magnetic effects, and the behavior of complex atoms required a deeper theory. The next clue came from Louis de Broglie. In 1924, de Broglie proposed that the wave and particle duality seen in light might also apply to matter. If light, long understood as a wave, could behave like particles, perhaps particles such as electrons could display wave-like properties. De Broglie related the wavelength of a particle to its momentum. The relationship can be expressed as wavelength equals Planck's constant divided by momentum. This idea offered a possible explanation for Bohr's permitted states. A stable electron state could behave like a standing wave around the nucleus. Only wavelengths that fitted consistently into the atomic structure would be allowed. Other arrangements would interfere with themselves and fail to form stable patterns. The wave-like nature of electrons was confirmed experimentally by Clinton Davison and Lester Germer. In the 1920s, they directed electrons toward a crystal of nickel and measured how the electrons scattered. Crystals contain atoms arranged in regular repeating layers. Waves reflected from those layers can reinforce or cancel one another, producing a diffraction pattern. Davison and Germer observed just such a pattern with electrons. The measured wavelengths agreed with de Broglie's prediction. Electrons were not simply tiny classical balls. They could produce interference and diffraction, unmistakable features of waves. A complete quantum mechanics soon emerged in several mathematical forms. Werner Heisenberg developed matrix mechanics, which focused on measurable quantities and the transitions between quantum states. Erwin Schrödinger developed wave mechanics, describing quantum systems through a wave function that evolved according to the Schrödinger equation. Although these approaches looked very different, they were shown to be mathematically equivalent. Max Born then provided the probability interpretation of the wave function. The wave function did not describe an ordinary material wave spread through space in the same way as water or sound. Its magnitude was used to calculate the probabilities of possible measurement outcomes. The electron in an atom was no longer assigned a definite miniature orbit. Instead, it occupied a quantum state. That state could provide probabilities for where the electron might be detected, values for its energy and angular momentum, and predictions for how it would respond to physical interactions. Werner Heisenberg also formulated the uncertainty principle. This principle states that certain pairs of physical quantities, including position and momentum, cannot both possess arbitrarily sharp values in the same quantum state. It is often described as though the electron has a perfectly definite position and momentum that our instruments simply disturb or fail to reveal. That is not the central meaning. The uncertainty arises from the structure of quantum states themselves. A state concentrated very narrowly in position must contain a wider range of possible momenta, while a state with sharply defined momentum must be spread more broadly in position. Quantum mechanics therefore replaced the old demand for exact hidden paths with a different framework built from wave functions, quantum states, probabilities, observables, and permitted measurement outcomes. Atomic stability followed naturally from these quantum rules. Electrons could occupy lowest energy states that did not radiate away their energy like classical orbiting charges. Their wave-like nature restricted the states available to them. Quantization prevented energy from changing through an unlimited continuum of arbitrary values. An electron could not simply settle motionless inside the nucleus either. Confining it to an extremely small region would require a very broad range of momentum and therefore a large amount of kinetic energy. The quantum state of lowest total energy instead spreads through a region around the nucleus. Stable atoms are not miniature solar systems held together by classical balance alone. They are quantum systems whose structure depends on allowed energies, wave-like behavior, probability distributions, and fundamental limits on what can be sharply defined at once. Classical physics revealed the nucleus but could not explain why matter survived around it. Quantum mechanics supplied the missing rules. In doing so, it preserved the atom, explained its light, and replaced the neat planetary picture with something stranger, less visual, and far more accurate. An atom is not a miniature machine with electrons travelling along neat circular tracks. It is a quantum system, and its internal structure is described through mathematical objects that do not behave like familiar solid things. The most important of these is the wave function. A wave function contains the information needed to calculate the probabilities of possible outcomes when a quantum system is measured. For an electron in an atom, it can be used to predict the likelihood of detecting the electron in different regions, the energies that may be observed, and the possible values of properties such as angular momentum. It is tempting to imagine the wave function as a blurry cloud of ordinary material, as though the electron were simply smeared out because our view is imperfect. That picture is misleading. The wave function is not merely a fuzzy photograph of a classical particle following an unknown path. It describes a genuinely quantum state, and quantum mechanics does not generally assign the electron one definite hidden position and momentum at every moment in the classical sense. When physicists calculate the possible states of electrons bound to atomic nuclei, they find particular patterns known as atomic orbitals. An orbital is not an orbit. It is not a route that an electron repeatedly follows around the nucleus. Instead, an orbital is a quantum state with a characteristic energy, angular momentum, spatial probability distribution, and mathematical shape. The familiar pictures of spherical and lobed orbitals show regions where an electron in a particular state is more or less likely to be detected. The simplest orbital is spherically symmetric around the nucleus. Other orbitals form pairs of lobes, more elaborate clusters, or shapes containing regions where the probability of finding the electron falls to zero. These shapes arise from solutions to the Schrödinger equation. The nucleus attracts the negatively charged electron through the electromagnetic interaction, while the electron's wave-like nature restricts the stable patterns that can exist around it. Only certain quantum states satisfy the necessary conditions, producing discrete energies rather than an unlimited continuum. Electron states are identified using quantum numbers. The principal quantum number is associated mainly with the overall energy level and typical size of the orbital. Larger principal quantum numbers generally correspond to states extending farther from the nucleus and possessing greater energy. A second quantum number describes orbital angular momentum. It distinguishes broad orbital families that are traditionally labelled with letters, although the underlying idea is more important than the labels themselves. Different values correspond to different spatial structures and angular properties. A third quantum number describes the orientation of the orbital angular momentum relative to a chosen direction. This becomes especially important when an atom is placed in a magnetic field, because states with different orientations can respond differently. The electron also possesses spin. Spin behaves mathematically like a form of intrinsic angular momentum, but the word can easily create the wrong image. An electron is not thought to be a tiny solid sphere rotating around its own axis. If it were, the classical surface speed required to reproduce its measured properties would lead to serious physical contradictions. Spin is instead a fundamental quantum property. For an electron, measurements of spin along a chosen direction produce one of two possible values. These are often described as spin up and spin down, although they do not mean that a little object is literally pointing upward or downward before every measurement. Electron spin plays a central role in the structure of matter because electrons belong to a quantum category known as fermions. In 1925, Wolfgang Pauli formulated the exclusion principle, which states that two identical fermions cannot occupy the same complete quantum state. Inside an atom, this means that two electrons may share the same spatial orbital only if their spin states differ. Once those possibilities are filled, additional electrons must occupy different states, often with greater energy or different angular structure. The exclusion principle creates the layered arrangement of electrons into shells and subshells. The lowest available states fill first, although the precise ordering in larger atoms depends on the energies produced by electron interactions and nuclear attraction. Hydrogen contains one electron and therefore occupies the simplest arrangement. Helium contains two electrons, which can share the lowest spatial orbital because they possess opposite spin states. The next electron, found in lithium, cannot enter the same complete state and must occupy a higher energy level. As atomic number increases, the available states fill in a systematic pattern. This quantum structure underlies the periodic table. Elements in the same column often possess similar arrangements of outer electrons, which helps explain why they display related chemical behavior. The outermost electrons are known as valence electrons. They are generally the electrons most directly involved in chemical bonding, because they are less tightly bound than electrons closer to the nucleus. The number and arrangement of valence electrons strongly influence whether an atom tends to lose electrons, gain them, share them, or remain comparatively unreactive. An atom naturally tends toward its lowest available energy arrangement, known as the ground state. If it absorbs energy, one or more electrons may move into an excited state. This absorbed energy may come from a collision, heat, an electric current, or a photon with the correct energy. Because the allowed energies are quantized, the atom cannot absorb just any arbitrary amount through a simple transition. The incoming energy must match the difference between permitted states closely enough for the interaction to occur. An excited state is usually temporary. When an electron moves into a lower energy state, the atom may emit a photon. The photon carries an energy equal to the difference between the two atomic levels. Since each element possesses its own internal pattern of permitted energies, it produces a characteristic set of spectral lines. These spectra act like atomic fingerprints. By analyzing light from a laboratory flame, a distant star, or a cloud of interstellar gas, scientists can identify the elements present even when the matter itself cannot be collected. Stable atomic states also explain why electrons do not continuously radiate energy and spiral into the nucleus. In classical physics, an orbiting charged particle accelerates and emits radiation. In quantum mechanics, an electron occupying a stationary energy eigenstate does not behave like a charged bead circling along a definite trajectory. The probability distribution associated with such a state remains stable over time. The state has a definite energy, and there is no continuous stream of lower and lower orbital energies available into which the electron can slide. Radiation is connected with transitions between quantum states, not with a classical orbit steadily shrinking. Quantum states can also exist in superposition. A superposition is a combination of different possible states, each contributing to the overall wave function. An electron may therefore be prepared in a state that is not associated with one single, definite value of a particular observable. When the system interacts strongly with a measuring device or its surrounding environment, a definite result is recorded. Repeating the same preparation many times produces outcomes with frequencies predicted by the wave function. The interpretation of exactly what occurs during measurement remains debated, but the statistical predictions are extraordinarily successful. Another striking feature of the quantum architecture is tunneling. In classical physics, a particle without enough energy to cross a barrier must remain trapped. Quantum mechanics assigns a wave function that may extend through and beyond the barrier, creating a non-zero probability that the particle will be detected on the other side. Quantum tunneling contributes to alpha decay, in which a particle escapes from an atomic nucleus despite facing a classically forbidden energy barrier. It also plays a role in nuclear fusion inside stars, allowing positively charged nuclei to approach closely enough to interact even when their thermal energies would rarely overcome the full electromagnetic repulsion in a classical picture. The scanning tunneling microscope uses the same principle. When an extremely sharp conducting tip is brought very close to a surface, electrons can tunnel through the narrow gap. The resulting current changes sharply with distance, allowing individual atoms on a surface to be mapped with remarkable precision. An atom is therefore not a hard outer shell enclosing a miniature empty chamber. It is a stable arrangement involving a compact nucleus, quantum electron states, probability distributions, electromagnetic interactions, and the exclusion principle. Its architecture is not visible in the ordinary sense, yet it determines almost everything matter can become. The available electron states shape the periodic table. The outer electrons govern chemical bonding. Quantist transitions produce light. Tunneling enables processes that classical physics would forbid. The ordinary atom is not simple because it is small. It is stable because its parts obey a carefully structured quantum order, one that replaces definite paths with permitted states and turns the foundations of matter into a quiet architecture of probabilities. Atoms rarely remain isolated for long. Their electrons interact with the electrons and nuclei of nearby atoms through the electromagnetic force, creating attractions and repulsions that can produce stable arrangements. When the combined system can settle into a lower energy configuration than the separated atoms possessed, a chemical bond may form. This does not mean that atoms consciously seek low energy, rather like tiny creatures looking for a comfortable chair. It means that physical systems tend to occupy stable arrangements when energy can be released into the surroundings. Once formed, a bond may require additional energy to break, because separating the atoms would move the system into a less favourable state. The electrons most involved in bonding are generally the outer, or valence electrons. Inner electrons remain more tightly bound to their own nuclei, while outer electron states extend farther into the surrounding region and can interact more strongly with neighbouring atoms. One major form of bonding is the covalent bond. In a covalent bond, electron density is shared across two or more atomic nuclei. The electrons are not necessarily divided into neat halves or passed repeatedly from one atom to another. Instead, the separate atomic states combine into molecular quantum states that belong to the molecule as a whole. The simplest example is the hydrogen molecule. Each isolated hydrogen atom contains one proton and one electron. When two hydrogen atoms approach, their atomic orbitals begin to overlap. The electron wave functions can combine in more than one way. In one combination, known as a bonding molecular orbital, electron density is increased in the region between the two nuclei. Each negatively charged electron is attracted to both positive nuclei, helping hold the system together. The concentration of electron density between the nuclei reduces the total energy, creating a stable bond at an appropriate separation. The atomic orbitals can also combine into an antibonding molecular orbital. In this state, the wave functions interfere so that electron density is reduced between the nuclei. Occupying the antibonding state weakens the connection and can prevent a stable bond from forming. The hydrogen molecule is stable because its two electrons can occupy the lower energy bonding orbital with opposite spin states. If the antibonding orbital were equally filled, the stabilizing and destabilizing effects would largely cancel. The diagrams used in chemistry often show a straight line between two atoms. This is convenient shorthand, but there is no microscopic stick connecting the nuclei. The bond is an extended quantum arrangement involving electron density, electromagnetic attraction, nuclear repulsion, electron repulsion, and the allowed states of the complete system. Covalent bonds create much of the molecular variety found in ordinary matter. Oxygen atoms bond to one another in the oxygen molecules present in air. Carbon forms strong bonds with itself and with many other elements, producing chains, rings, sheets, and three-dimensional frameworks. Carbon's bonding versatility is one reason it plays such a central role in biological chemistry. Electron sharing is not always equal. Different elements attract shared electron density with different strengths. This tendency is described by electronegativity, a concept developed and organized extensively by the American chemist Linus Pauling. When two identical atoms form a covalent bond, the electron distribution is usually shared symmetrically. When different atoms bond, one may attract the electrons more strongly. The resulting bond is called a polar covalent bond. Water provides a familiar example. Oxygen attracts the shared electrons more strongly than hydrogen does. The oxygen side of the molecule therefore carries a partial negative charge, while the hydrogen side carries a partial positive charge. The molecule remains electrically neutral overall, but its charge is distributed unevenly. This separation creates a molecular dipole. A dipole has a more positive region and a more negative region, allowing neighbouring molecules to attract one another through permanent dipole interactions. The precise shape of the molecule matters because individual bond polarities may reinforce or cancel one another depending on their orientation. If the difference in electron attraction becomes sufficiently strong, bonding may be described as largely ionic. In an idealized ionic bond, one atom loses one or more electrons and another gains them. The atom that loses electrons becomes a positively charged ion, while the atom that gains them becomes a negatively charged ion. Opposite charges attract through the electromagnetic force. Sodium chloride, ordinary table salt, is a standard example. A sodium atom can lose an outer electron, while a chlorine atom can gain one. The resulting sodium and chloride ions carry opposite electric charges. A salt crystal, however, is not best pictured as a collection of separate sodium chloride molecules sitting side by side. It forms an extended three-dimensional lattice. Each ion is surrounded by several oppositely charged neighbours, and the electrostatic attraction extends throughout the crystal. The lattice is stable because the attractive interactions between opposite charges outweigh the repulsions at the equilibrium spacing. Pushing ions too closely together produces strong repulsion, while separating them requires energy because the attractive arrangement must be disrupted. The distinction between covalent and ionic bonding is not always absolute. Real bonds often contain elements of both. Electron density may be strongly shifted without being completely transferred, and the most accurate description depends on the full quantum state of the material. Metals form another distinctive type of structure. In metallic bonding, many valence electrons are delocalized across a lattice of positively charged ion cores. Rather than belonging permanently to one particular atom or bond, these electrons occupy extended quantum states throughout the material. This delocalization helps explain why metals conduct electricity. When an electric field is applied, mobile electrons can respond and produce an electric current. They also transport thermal energy efficiently, contributing to the high thermal conductivity of many metals. Metallic bonding also helps produce malleability and ductility. Layers of ion cores can shift relative to one another without necessarily breaking a fixed network of directional bonds. The delocalized electrons continue to bind the structure as it changes shape. A metal can therefore be hammered into a sheet or drawn into a wire without immediately crumbling. Atoms and molecules also interact through forces weaker than the main bonds holding molecules together. These intermolecular forces are individually modest, yet they become extremely important when many interactions act at once. Hydrogen bonding occurs when hydrogen is covalently bonded to a strongly electronegative atom, commonly oxygen, nitrogen or fluorine, and is attracted to an electron-rich region of a neighbouring molecule. A hydrogen bond is weaker than a typical covalent bond, but it is often stronger and more directional than many other intermolecular attractions. Water owes many of its unusual properties to hydrogen bonding. Water molecules form a fluctuating network of attractions that continually break and reform. This helps produce water's comparatively high boiling point, its strong surface tension, and the open crystal structure of ice. Because solid ice is less dense than liquid water, it floats. This seemingly ordinary fact has enormous consequences for lakes, oceans, weather, geology, and life. A weak molecular interaction, repeated across uncountable numbers of molecules, can influence the behaviour of an entire planet. Permanent dipole interactions also occur between polar molecules. The more positive region of one molecule attracts the more negative region of another. Thermal motion constantly changes the orientations, so the molecules do not usually lock into one perfect arrangement, but the average attraction still affects boiling points, solubility, and material structure. Even atoms and molecules with no permanent dipole can attract one another through London dispersion forces. Electron distributions fluctuate because quantum particles are never arranged as perfectly fixed classical charges. At one instant, a temporary unevenness in one atom may create a small dipole. This fluctuating dipole can distort the electron distribution of a neighbouring atom, producing an induced dipole. The two temporary charge patterns then attract. The effect is usually weak for small particles, but grows stronger in larger, more easily distorted electron clouds. London dispersion forces help liquefy noble gases, stabilise molecular crystals, and contribute to interactions between large biological molecules. They also play a role in the remarkable adhesion of geckos. The toes of a gecko contain vast numbers of microscopic hairs, which divide into even finer structures. These make extremely close contact with the surface over a large combined area. Dispersion forces between the toe structures and the surface are weak individually, but together they produce enough attraction to support the animal's weight. Weak interactions are equally important in biology. Proteins fold into specific shapes through a combination of hydrogen bonds, charge interactions, dispersion forces, and the behaviour of molecules in water. The final structure determines whether the protein can transport oxygen, catalyse a reaction, transmit a signal, or form part of a cell. Molecular shape is therefore not a decorative detail. It arises from the arrangement of electron states, the positions of nuclei, electrostatic repulsion, bonding patterns, and the drive toward lower total energy. Electrons in bonds occupy regions of space, and those regions influence how atoms arrange themselves. A water molecule is bent rather than perfectly straight. Methane forms a three-dimensional tetrahedral arrangement. Carbon dioxide is linear. These geometries affect polarity, reactivity, melting point, boiling point, biological function, and the larger structures molecules can create. Chemical reactions occur when atoms exchange partners and their electrons reorganize into new bonding arrangements. Existing bonds may break, new bonds may form, and energy may be absorbed or released. The identities of the atomic nuclei usually remain unchanged. This distinguishes chemical reactions from nuclear reactions. Burning wood, digesting food, rusting iron, and charging a battery involve electrons and chemical bonds. Nuclear fusion, nuclear fission, and radioactive decay alter atomic nuclei and can transform one element into another. The energy scale is also generally different. Chemical bond energies are typically measured in electron volts per molecule, while nuclear changes commonly involve millions of electron volts per nucleus. Nuclear reactions can therefore release vastly more energy for a given amount of material. The diversity of matter does not require an equally vast number of fundamental ingredients. A relatively modest set of chemical elements can be combined in different proportions, shapes, bonding patterns, electronic states, and extended structures. The same carbon atoms can help form soft graphite, hard diamond, flexible biological molecules, fuels, plastics, and living tissue. Hydrogen and oxygen can form water, while different arrangements involving those elements and others produce entirely different substances. Matter becomes varied not only because of what it contains, but because of how its parts are organized. Atoms become molecules through quantum states and electromagnetic interactions. Molecules then gather into structures whose collective properties may look almost unrelated to the individual atoms from which they began. The world's chemical richness is therefore a story of arrangement. From a small alphabet of elements, physical laws assemble an immense language of substances, each created by the quiet architecture of electrons shared, transferred, distributed, and drawn into stable patterns around atomic nuclei. Place your hand on a table, or simply notice the floor supporting your weight. The experience feels completely ordinary. Your hand stops at the surface. Your feet do not pass through the ground. The table does not collapse into the material beneath it. Solid objects seem to possess an obvious ability to resist one another. But what is actually doing the resisting? At the atomic scale, there are no perfectly hard outer walls. An atom is not a tiny marble with a rigid surface. Its nucleus is extremely small, while its electrons occupy quantum states spread through a much larger surrounding region. When two solid objects approach one another, their atoms do not collide like rows of miniature billiard balls. Instead, the electron distributions of the two materials begin to interact. Electrons carry negative electric charge. As the atoms in your hand approach the atoms in the table, the negatively charged electron distributions repel one another through the electromagnetic force. The positively charged nuclei also interact with the surrounding electrons, and the total response depends on the complete arrangement of charges within both materials. At ordinary distances inside matter, attractions and repulsions are already balanced in stable atomic and molecular structures. Pushing two objects together disturbs that balance. The atoms are forced slightly closer than their preferred spacing, and the electromagnetic energy of the system rises. The material responds by pushing back. This electromagnetic repulsion is one major part of the contact force you feel, but it is not the entire story. Quantum mechanics adds another powerful source of resistance through the Pauli exclusion principle. Electrons belong to a class of quantum particles called fermions. Wolfgang Pauli's exclusion principle states that identical fermions cannot occupy the same complete quantum state. Two electrons may share the same spatial orbital only when another property, such as their spin state, distinguishes them. They cannot all collapse into one identical low-energy arrangement. This matters enormously inside solid materials. When atoms are compressed, their electron states begin to overlap more strongly. The electrons cannot simply gather into the same available states without restriction. Some must occupy different states, often involving greater momentum and higher energy. Forcing matter into a smaller volume therefore becomes increasingly difficult. Electromagnetic interactions oppose the crowding of charges, while the exclusion principle limits how identical electrons can be arranged. Together, these effects create a strong resistance to compression. The solidity of a table is not located inside any single electron or atom. It is a collective property of an enormous quantum system. A lone atom is not a tiny piece of hardness. Solidity emerges when countless atoms form stable structures and respond together when pressure is applied. When your hand rests on a table, the upward support exerted by the table is called the normal force. The word normal here means perpendicular. The table exerts a force perpendicular to its surface, balancing the downward forces acting on your hand. At a human scale, this seems like one smooth push. Microscopically, it results from electromagnetic and quantum interactions as the atoms in the two materials resist being moved into unfavorable arrangements. Your hand presses slightly into the table, and the table bends or compresses by an extremely small amount. its atoms shift from their equilibrium positions, producing forces that push them back. Even materials that appear completely rigid deform under pressure. A wooden desk, a steel beam, and a concrete floor all change shape when a force is applied. The changes may be too small for the eye to notice, but they are real and measurable. Within a solid, atoms or molecules occupy positions determined by the balance of attractive and repulsive interactions. If they are moved slightly closer together or farther apart, the energy of the system increases. Forces then act in directions that tend to restore the original spacing. This restoring behavior produces elasticity. An elastic material changes shape under an applied force and then returns toward its earlier form when that force is removed. During the 17th century, Robert Hooke investigated springs and other elastic systems. The relationship associated with his work is commonly known as Hooke's law. Within a limited range, the amount a spring stretches or compresses is approximately proportional to the force applied. This can be stated in spoken form as the restoring force is proportional to the displacement from equilibrium. The relationship is useful, but it is not universal. It applies only while the material remains within its elastic range. Stretch a spring gently, and it returns to its previous shape. Pull it too far, and its internal structure changes permanently. At that point, the simple proportional relationship no longer describes the behavior accurately. Elastic deformation involves atoms shifting slightly, while their overall arrangement remains capable of returning to its lower energy structure. Plastic deformation is different. In plastic deformation, parts of the material move into new arrangements that do not fully reverse when the force is removed. In crystalline solids, layers of atoms may slide past one another along particular directions. Defects called dislocations can move through the crystal, allowing the material to change shape without every bond breaking at once. This helps explain why metals can be bent, hammered, rolled, or drawn into wires. Once these internal rearrangements have occurred, the material may remain bent. The atoms have not returned to precisely the same pattern they occupied before. The deformation has become permanent. If the applied stress becomes great enough, cracks may form and spread. Bonds break near the crack tip, and the material separates. Brittle materials such as glass may fracture with relatively little plastic deformation, while ductile materials such as many metals can change shape considerably before breaking. The sensation of solidity is also closely connected with friction. When one surface slides across another, resistance appears along the direction of motion. It is tempting to imagine friction as nothing more than tiny bumps catching against one another, like microscopic mountains scraping across a landscape. Surface roughness does contribute, but the full process is more complicated. Even polished surfaces contain irregularities when examined closely. The highest microscopic points, known as asperities, make contact first. Under pressure, these small contact regions may deform. Some may flatten, bend, or break as the surfaces move. Adhesion also matters. At places where atoms from the two surfaces come extremely close, electromagnetic interactions can produce temporary attractions. Small junctions may form and then rupture during sliding. Molecular interactions, contaminants, moisture, surface chemistry, and temperature can all alter the resulting friction. Energy is transferred throughout this process. The organized motion of the sliding object becomes disordered microscopic motion within the materials. Atoms vibrate more strongly, and the surface is warm. Friction therefore converts mechanical energy into internal energy, usually experienced as heat. When you rub your hands together, the warmth does not appear because matter is being destroyed. Ordered motion is being redistributed into the irregular motion and vibration of vast numbers of particles. It is sometimes said that two hands never truly touch. There is a useful idea hidden in this statement, but it can also become misleading. The atoms in one hand do not merge with the atoms in the other, and their nuclei remain separated by enormous distances compared with nuclear dimensions. The outer electron distributions interact electromagnetically, while quantum rules resist further overlap. However, this interaction is precisely what physical contact means. Contact does not require perfectly rigid surfaces to become geometrically fused. It means that two material systems have approached closely enough for strong short-range electromagnetic and quantum effects to transfer force, energy, and information between them. The sensation in the skin begins when contact forces deform tissues and activate specialized sensory receptors. These receptors generate electrical signals that travel through nerves to the brain. The feeling of pressure is therefore grounded in real atomic interactions, even though the experience itself is constructed by the nervous system. The resistance of ordinary solids becomes even more striking when compared with matter under extreme compression. A neutron star forms when the core of a massive star collapses under gravity. The pressure becomes so intense that electrons and protons can combine through weak interaction processes, producing matter dominated by neutrons. A neutron star can contain more mass than the Sun within a sphere only about the size of a city. Its density is so great that a tiny volume of its material would possess an extraordinary mass under Earth-like conditions. Gravity in such an object is vastly stronger than anything acting on an ordinary table. Yet the star does not immediately collapse without limit. Quantum degeneracy pressure associated with fermions, together with strong nuclear interactions, helps resist further compression. Degeneracy pressure does not arise from particles behaving like compressed rubber balls. It results from the exclusion principle. As fermions are forced into a smaller region, available low-momentum quantum states fill, and additional particles must occupy states with greater momentum. This generates a powerful resistance to further confinement. In ordinary solids, electron behavior and electromagnetic interactions create the resistance that supports everyday objects. In white dwarf stars, electron degeneracy pressure becomes central. In neutron stars, neutron degeneracy and nuclear interactions operate under far more extreme conditions. The underlying quantum rules remain related, even though the scale and intensity change dramatically. Solidity is therefore not a basic substance hidden inside atoms. It is a stable pattern of response. It arises from electromagnetic forces, quantum states, atomic structure, molecular bonding, and the exclusion principle acting across immense numbers of particles. The table feels solid because its atoms are organized into a structure that strongly resists deformation. The floor supports you because its particles cannot simply be compressed into identical states or pushed through one another without a large increase in energy. Matter feels firm and continuous, but the firmness is an emergent achievement. Every solid surface quietly maintains a balance of forces and quantum restrictions, creating the dependable world that holds its shape beneath your hands and feet. Matter can appear rigid, fluid, weightless, dense, transparent, or glowing, yet these different states do not require different fundamental ingredients. A solid, a liquid, and a gas may all be made from exactly the same molecules. What changes is the way those molecules are arranged, how freely they move, and how strongly they interact. States of matter are therefore large-scale patterns of organization and motion. They emerge from the collective behavior of enormous numbers of particles rather than from each particle carrying a label that says solid, liquid, or gas. Water provides the most familiar example. Ice, liquid water, and water vapor are all composed mainly of water molecules. The molecules themselves do not become new fundamental objects when the state changes. Instead, their average spacing, motion, and pattern of interaction are altered. In a solid, atoms, ions, or molecules remain close to relatively stable positions. They still move. Even in a solid block of material, particles vibrate because they possess thermal and quantum energy. What makes the material solid is that its internal structure resists lasting changes in shape. Many solids are crystalline. In a crystal, the particles occupy a repeating arrangement that extends across large distances compared with the size of an atom. Table salt forms a regular lattice of sodium and chloride ions. Diamond contains carbon atoms connected in a strong three-dimensional network. Metals contain ordered arrays of atomic cores surrounded by delocalized electrons. The repeating structure of a crystal can strongly influence its properties. It can determine how the material breaks, how it conducts electricity, how it transmits light, and how easily layers of atoms can slide past one another. Not all solids possess this long-range order. Ordinary window glass is an amorphous solid. Its atoms are held in a rigid arrangement, but they do not form one repeating crystal pattern across the entire material. The local structure may contain some order, yet the larger arrangement is comparatively irregular. Glass is sometimes described as a liquid that flows extremely slowly. This is misleading for ordinary glass under everyday conditions. It behaves as a solid and does not gradually sag in the way often claimed. Uneven thickness in old windows usually reflects historical manufacturing methods rather than centuries of downward flow. In a liquid, particles also remain close together. This is why liquids are difficult to compress. There is relatively little empty separation available to remove. However, the particles are not locked into fixed long-term positions. They continually move, rotate, and exchange neighbours. This allows a liquid to flow and adopt the shape of its container while retaining a nearly fixed volume. The local structure is constantly reorganizing. In liquid water, hydrogen bonds form and break on extremely short timescales, creating a fluctuating network rather than a permanent arrangement. A gas behaves differently because its particles are generally much farther apart. They move throughout the available volume and interact strongly mainly during collisions, at least in a simple idealized description. A gas therefore expands to fill its container and can be compressed far more easily than a liquid or solid. Gas pressure arises from momentum being transferred during collisions. Molecules strike the walls of a container and change direction. The wall receives the corresponding momentum, producing a force. The combined effect of an enormous number of collisions creates the steady pressure measured by an instrument. Temperature is closely connected with microscopic energy, but it should not be reduced to the speed of one particle. In a gas, particles possess a distribution of speeds. Some move relatively slowly, others much faster, and collisions continually exchange energy among them. Temperature describes a statistical property of the whole system. It is related to how energy is distributed among the available microscopic motions and states. In simple gases, higher temperature generally corresponds to greater average translational kinetic energy, but real materials can also store energy in rotation, vibration, electronic states, and interactions between particles. The kinetic theory of gases connects these microscopic motions with large-scale measurements. In an ideal gas, pressure increases when particles strike the container walls more frequently, or transfer more momentum during each collision. The ideal gas relationship can be written in spoken form as pressure multiplied by volume equals the number of particles multiplied by Boltzmann's constant multiplied by temperature. This relation shows how pressure, volume, particle number, and temperature are connected. If a sealed gas is heated while its volume remains fixed, its pressure rises. If the container expands while temperature remains constant, the pressure falls. Real gases depart from the ideal model when particles interact strongly or occupy a significant fraction of the available volume. A state change occurs when temperature, pressure, or another condition alters the balance between microscopic energy, intermolecular attraction, and collective order. During melting, a solid absorbs energy and loses enough structural order for its particles to move past one another. The material becomes liquid. During freezing, energy is released, and the particles settle into a more rigid arrangement. Boiling changes a liquid into a gas throughout its volume. Vapor bubbles form within the liquid when the vapor pressure becomes comparable to the surrounding pressure. These bubbles rise, expand, and escape. Evaporation is different. It can occur at the surface of a liquid even below the boiling point. Some molecules near the surface happen to possess enough energy and the right direction of motion to escape into the gas above. Because the more energetic molecules are more likely to leave, evaporation can cool the remaining liquid. This is why perspiration helps cool the body, and why wet skin may feel chilly even in reasonably warm air. Condensation is the reverse process. Gas particles lose enough energy to gather into a liquid. Water droplets forming on a cold glass are produced when water vapor in the surrounding air condenses on the cooler surface. Sublimation occurs when a solid changes directly into a gas without first becoming liquid. Dry ice, made from solid carbon dioxide, sublimes under ordinary atmospheric conditions. Deposition is the reverse transition, in which gas becomes solid directly. Frost can form when water vapor deposits as ice on a sufficiently cold surface. During many phase changes, energy can enter or leave a substance without immediately changing its temperature. This energy is known as latent heat. When ice melts at a fixed pressure, incoming energy is used mainly to disrupt the ordered solid structure and alter intermolecular arrangements. The temperature can remain near the melting point until the transition is complete. Similarly, boiling water can continue absorbing substantial energy while remaining close to its boiling temperature because the energy is being used to separate molecules into the gas phase. Entropy also helps explain these changes. A liquid usually has more accessible microscopic arrangements than a crystal, while a gas has far more possible positions and motions than either. Greater disorder is an imperfect everyday description, but the deeper idea concerns the number of microscopic configurations compatible with the large-scale state. At low temperature, energy considerations may favor an ordered solid. At higher temperature, the growing importance of entropy may favor a liquid or gas. The observed phase depends on the balance between energy and the number of available microscopic arrangements. Pressure can change that balance as well. Increasing pressure generally favors denser phases, although water provides an important exception near ordinary conditions because ice is less dense than liquid water. This is one reason pressure can lower the melting point of ice. The phase diagram of a substance maps which state is stable under different combinations of temperature and pressure. Within such a diagram lies the triple point where solid, liquid, and gas can coexist in equilibrium. There is also a critical point. Above the critical temperature and pressure, the distinction between liquid and gas disappears. The substance becomes a supercritical fluid, possessing properties of both. It may spread through a container like a gas while dissolving materials more like a liquid. The familiar classroom trio of solid, liquid, and gas is only the beginning. Plasma is often described as another major state of matter. It forms when enough atoms become ionized, separating electrons from atomic nuclei and creating a mixture of free charged particles. Because these charges respond collectively to electric and magnetic fields, plasma can behave very differently from an ordinary neutral gas. It can carry electric currents, form filaments, generate magnetic structures, and support complex waves. Stars are composed largely of plasma. Lightning briefly creates plasma in the atmosphere. Auroras arise when charged particles interact with gases high above Earth, producing glowing, ionized regions. Plasma is also created and controlled in laboratory devices, including experimental fusion reactors. Many more specialized phases exist. Liquid crystals combine fluid motion with partial molecular order and are used in display technologies. Superfluids can flow with extraordinarily low resistance. Superconductors carry electric current without ordinary electrical resistance below a critical temperature. Bose-Einstein condensates form when certain particles are cooled so strongly that many occupy a shared quantum state, allowing quantum behavior to become visible across an entire cloud of atoms. Matter does not possess one fixed style of organization. The same particles can assemble into radically different collective states depending on temperature, pressure, density, interaction strength, and quantum rules. A block of ice, a glass of water, and a cloud of vapor are not different because their molecules have forgotten what they are. They differ because the same molecular ingredients have settled into different patterns of spacing, motion, energy, and order. What appears at the human scale as rigidity, flow, expansion, boiling or freezing is the visible expression of countless microscopic particles continually balancing attraction, motion, probability and structure. A solid object may look perfectly still, yet its interior is never truly inactive. Atoms vibrate, molecules rotate, electrons occupy changing states, and energy is continually exchanged through countless microscopic interactions. The calm appearance of matter hides an immense statistical life. Even a tiny visible sample contains an extraordinary number of particles. A glass of water holds far more molecules than anyone could track individually. Each molecule possesses several possible forms of motion, including movement through space, rotation, vibration, and interaction with neighboring molecules. Physicists refer to these independent possibilities as degrees of freedom. The underlying physical laws may be precise, but following every particle separately would be practically impossible. Fortunately, large collections of particles display stable statistical patterns. Thermodynamics and statistical mechanics describe these patterns, allowing pressure, temperature, energy, and entropy to be predicted without knowing the exact path of every atom. Early versions of this microscopic picture appeared long before atoms were universally accepted. During the 18th century, Daniel Bernoulli proposed that gas pressure could be explained by particles moving rapidly and colliding with the walls of a container. The visible pressure of the gas emerged from innumerable invisible impacts. During the 19th century, Rudolf Clausius developed important concepts in thermodynamics and kinetic theory. He helped clarify the relationship between heat, molecular motion, work, and entropy. Ludwig Boltzmann later connected thermodynamic behavior with probability, showing how large-scale regularity could arise from microscopic motion. To understand this statistical view, it helps to separate three ideas that are often blended together: internal energy, temperature, and heat. Internal energy is the total microscopic energy stored within a physical system. It can include the translational motion of particles, molecular rotation, atomic vibration, electronic excitation, chemical bonding, and interaction energy between particles. In a complex material, internal energy is distributed across many different microscopic forms. Temperature describes how energy is statistically distributed among the accessible states of a system. In a simple gas, it is closely related to the average translational kinetic energy of the particles. In solids, liquids, and more complicated systems, energy may also be stored in vibration, rotation, electronic structure, and collective motion. Temperature is therefore not the speed of one individual molecule. At any given temperature, particles usually possess a range of energies and speeds. Some may be moving comparatively slowly, while others move far faster than the average. Heat is not a substance stored inside a warm object. Heat is energy transferred between systems because of a temperature difference. Once the energy has entered a system, it becomes part of that system's internal energy. A hot drink left in a cool room transfers energy to its surroundings. The drink loses internal energy, while the nearby air, cup, table, and room gain it. The process continues until the temperature difference becomes small enough for thermal equilibrium to be reached. Energy can move through matter in several important ways. Conduction transfers energy through interactions among neighboring particles. In a solid, atoms vibrating more energetically can disturb nearby atoms, passing energy through the structure. In metals, mobile electrons can also transport energy efficiently. These electrons move through extended states within the material and exchange energy with the atomic lattice, helping many metals conduct both heat and electricity well. Convection transfers energy through the large-scale motion of a fluid. When part of a liquid or gas is heated, its density may change, causing warmer material to rise and cooler material to sink. The resulting circulation transports energy through the fluid. Convection contributes to boiling water, atmospheric weather, ocean currents, and the motion of material inside stars. A saucepan and a star are rather different objects, but both can organize fluid motion through heating and gravity. Radiation transfers energy through electromagnetic waves. Unlike conduction and convection, radiation does not require matter between the source and the receiver. Energy from the sun crosses the vacuum of space as electromagnetic radiation before warming Earth. These transfers tend to move energy from concentrated organized forms into more widely distributed ones. This tendency is described through entropy and the second law of thermodynamics. Entropy is connected to the number and distribution of microscopic arrangements compatible with a system's visible large-scale condition. A macrostate is the overall state described by quantities such as temperature, pressure, and volume. A microstate is one particular detailed arrangement of the particles and their energies. Some macrostates can be produced by relatively few microscopic arrangements. Others can be produced in an overwhelmingly larger number of ways. An isolated system is therefore extraordinarily likely to evolve toward macrostates associated with more accessible microstates. This is the statistical meaning of the second law of thermodynamics. It does not say that every individual molecule must always move toward greater disorder. Small fluctuations can occur. Instead, it says that large systems overwhelmingly tend toward macroscopic conditions that are more probable, because they can be realized in more microscopic ways. Imagine two gases separated inside a container. When the barrier is removed, the gases mix. There is no fundamental law preventing every molecule from later returning to its original side, but the number of mixed arrangements is vastly greater than the number of neatly separated ones. Spontaneous remixing into the original pattern is therefore so improbable that it is never observed on an ordinary scale. The scent of perfume spreads through a room for the same reason. Molecules diffuse through the air until they are broadly dispersed. They do not normally gather themselves back into the bottle because the dispersed state can be realized through enormously more molecular arrangements. A warm drink cools because its energy spreads into the cooler environment. The reverse process, in which energy from the room spontaneously concentrates itself inside the drink, is not forbidden by simple energy conservation alone. It is rejected by overwhelming statistical improbability. Random thermal motion is not meaningless chaos. It is the visible result of countless collisions, forces, vibrations, and exchanges occurring too quickly, and in too many combinations to follow one by one. At the microscopic scale, particles continually transfer momentum and energy. At the macroscopic scale, their collective behavior becomes temperature, pressure, diffusion, and heat flow. Brownian motion offers a direct glimpse of this hidden activity. Tiny particles suspended in a liquid or gas move in an irregular, jittering way because surrounding molecules strike them unevenly from different directions. In 1905, Albert Einstein developed a quantitative explanation of Brownian motion based on molecular collisions. Jean Perrin later performed experiments that supported Einstein's predictions and provided strong evidence for the physical reality of atoms and molecules. Cooling matter reduces the thermal energy available to its microscopic degrees of freedom. The lowest possible thermodynamic temperature is called absolute zero. It corresponds to 0 Kelvin, or approximately minus 273 degrees Celsius. Absolute zero cannot be reached through a finite sequence of ordinary cooling steps. It is a limiting temperature rather than a conveniently available setting on a laboratory freezer. Quantum mechanics also prevents the simple conclusion that every particle becomes perfectly motionless at absolute zero. Many quantum systems retain 0-point energy, the minimum energy allowed by their quantum state. Confining a particle to a definite structure while assigning it exactly zero motion would conflict with the uncertainty principle. Thermal behavior is therefore an emergent balance of precise laws and statistical probability. The individual microscopic details may remain unknown, but large numbers make bulk matter remarkably predictable. These principles govern chemical reactions, engines, refrigerators, stars, weather systems, planetary atmospheres, and living organisms. A body remains organized by taking in useful energy and releasing heat and waste into its surroundings. A star converts nuclear energy into radiation. An engine transforms part of a temperature difference into mechanical work while dispersing the rest. Thermodynamics also gives physical processes a preferred direction. Heat flows naturally from hotter regions to colder ones. Gases spread. Energy disperses. Structures can still form, but only through processes that increase entropy elsewhere or consume concentrated energy. The stillness of matter is therefore only a large-scale impression. Beneath it lies ceaseless movement, collision, vibration, and redistribution. Out of that microscopic activity comes one of physics' quietest achievements. A world that remains statistically predictable even when its individual particles never stop moving. Electricity begins with electric charge, a fundamental property carried by particles. Electrons possess negative electric charge, while protons possess positive charge of exactly the same magnitude. Neutrons have no net electric charge. The signs positive and negative are conventions, but the difference between them is physically important because like charges repel, and opposite charges attract. The electric force between charged objects was measured carefully during the 18th century by Charles-Augustin de Coulomb. Coulomb showed that the strength of the force depends on the amount of charge present and decreases rapidly as the distance between the charges increases. The relationship can be stated as the electric force is proportional to the product of the charges and inversely proportional to the square of the distance between them. This inverse square behavior means that doubling the distance reduces the force to 1/4 of its previous strength. Tripling the distance reduces it to 1/9. At very small atomic distances, electric forces can therefore become extremely strong. Electric interactions are described through electric fields. An electric field is a physical quantity defined throughout space that indicates how a charged particle would be pushed or pulled at each location. A charged object creates an electric field around itself, and another charge responds to that field. This field description avoids the idea that one object must somehow reach across empty space instantaneously and tug directly on another. Changes in electromagnetic fields propagate through space at the speed of light, preserving the limits established by Albert Einstein's special theory of relativity. Ordinary matter contains immense quantities of electric charge. Every gram of material contains vast numbers of protons and electrons, yet most everyday objects are electrically neutral because their positive and negative charges almost exactly balance. Neutrality does not mean that charge is absent. It means that the total positive charge and total negative charge cancel when viewed on a large scale. Even a tiny imbalance can produce noticeable electrical effects because the underlying charges are so numerous. Static electricity appears when charge becomes unevenly distributed. Contact between different materials can transfer electrons from one surface to another. Separating the materials then leaves one with an excess of electrons and the other with a deficit. Friction can increase the amount of contact and separation, making the effect stronger, but it does not create electric charge from nothing. Charge is transferred and rearranged. Rubbing a balloon against hair, walking across a carpet, or removing certain synthetic clothing can separate enough charge to produce attraction, repulsion, or a small spark. Charge can also be redistributed by induction. A nearby charged object can push or pull the mobile charges inside another material without direct contact. One side may become relatively positive and the other relatively negative, even while the object remains neutral overall. Electric current is the organized movement of electric charge. In a metal wire, the main charge carriers are electrons already present within the material. When an electric field is established along the wire, these electrons develop a small average drift through their otherwise rapid and disordered motion. The drift speed of an individual electron is often surprisingly slow. Depending on the circuit, it may be only a fraction of a millimeter per second, or a few millimeters per second. Yet a lamp can respond almost immediately when a switch is closed. This happens because the electromagnetic influence that establishes the current propagates through the circuit at a substantial fraction of the speed of light. Electrons are already distributed throughout the wire, rather like water already filling a pipe. They do not need to travel individually from the switch to the lamp before the circuit responds. Whether charges can move easily depends on the quantum structure of the material. Conductors contain electronic states that allow electrons to respond readily to an applied electric field. Metals are common conductors because some of their electrons occupy extended states across the solid. Insulators behave differently. Their electrons are bound within filled energy states, and a substantial amount of energy is required to move them into states that can carry current. Under ordinary conditions, very little charge flows through materials such as glass, rubber, or dry ceramic. Semiconductors occupy an intermediate position. Their electrical behavior can be altered dramatically by temperature, light, applied voltage, or the deliberate addition of small quantities of other elements. These differences are explained through energy bands. When many atoms come together in a solid, their individual electron states interact. The enormous number of closely spaced states forms ranges of permitted energy known as bands. The valence band contains electronic states associated mainly with bonding. The conduction band contains higher energy states in which electrons can move more freely through the material. Between them may lie a band gap, a range of energy that contains no allowed electron states. In a conductor, a band may be only partly filled, or permitted bands may overlap, leaving nearby states available for electrons to enter when an electric field is applied. In an insulator, the valence band is full and separated from the conduction band by a large gap. In a semiconductor, the gap is smaller. A small amount of energy can therefore lift some electrons in a semiconductor into the conduction band. The missing electron states left behind in the valence band behave as mobile positive charge carriers called holes. The electrical behavior of a semiconductor can be controlled through doping. Doping means introducing carefully chosen impurity atoms into an otherwise pure crystal. These atoms add electronic states, or alter the number of available charge carriers. Some dopants provide additional electrons, creating material in which negative carriers dominate. Others create additional holes, producing material dominated by positive carriers. Joining these regions creates a junction with highly useful electrical behavior. Such junctions form the basis of diodes, which allow current to pass more easily in one direction than the other. More elaborate arrangements produce transistors, devices that can switch or amplify electrical signals. Billions of transistors can now be formed on a single integrated circuit. Their rapid switching enables processors, memory devices, sensors, phones, computers, and much of modern communication. The information age rests, quite literally, on carefully arranging atoms so that electrons have the right quantum states available to them. The deeper unity of electrical and magnetic behavior was established through the work of Michael Faraday and James Clerk Maxwell. Faraday showed experimentally that changing magnetic conditions could induce electric currents. He developed the physical idea of fields extending through space. Maxwell later expressed electricity and magnetism within one mathematical framework. His equations showed that changing electric fields generate magnetic fields, and changing magnetic fields generate electric fields. They also predicted electromagnetic waves travelling at the speed of light. Electricity and magnetism were therefore revealed as different aspects of one electromagnetic field. Light itself became part of the same physical story as charges, currents, magnets, and circuits. Real electrical currents also encounter resistance. In a conductor, electrons do not simply glide through a perfectly undisturbed crystal forever. They interact with vibrating atoms, impurities, defects, boundaries, and other excitations within the material. These interactions transfer energy from the organized motion associated with the current into less organized microscopic forms. The lattice vibrates more strongly, and the material warms. This is why wires, heaters, and electronic components can produce heat when current flows. Resistance is therefore not charge being used up. Electric charge is conserved. What changes is the form and distribution of energy. Ordered electrical energy becomes internal energy, light, sound, mechanical work, or other outputs. The electrical behaviour of matter depends on more than the identity of its atoms. Carbon can form insulating diamond, conducting graphite, and highly conductive graphene, because its atoms are arranged differently and provide different electronic states. Silicon becomes technologically useful not merely because it is silicon, but because it can be purified, crystallized, doped, layered, and patterned with extraordinary precision. Structure controls which electron states exist and how easily charges can move among them. Electricity inside matter is therefore the organized behavior of charged particles within a quantum landscape. The charges are fundamental, but the usefulness of a material comes from arrangement. Conductors, insulators, and semiconductors differ because their electrons are offered different possibilities. From a spark across a fingertip to the silent switching of a processor, electrical behavior emerges when matter guides charge through the energy states created by its own internal structure. Magnetism can seem like a separate and rather peculiar force. A magnet pulls on iron without touching it. A compass needle turns toward the north, and two magnetic poles can attract or repel across empty space. Yet magnetism is not an isolated feature of nature. It is part of the same electromagnetic interaction that produces electricity. Electric charges create electric fields. When those charges move, they also generate magnetic fields. A current flowing through a wire is therefore surrounded by a magnetic field, even though the wire itself may appear completely ordinary. This connection became unmistakable in 1820, when the Danish physicist Hans Christian Ørsted noticed that an electric current caused a nearby compass needle to move. Electricity was influencing magnetism. The result suggested that the two phenomena were linked rather than belonging to separate physical worlds. Michael Faraday later discovered the reverse relationship. A changing magnetic field could produce an electric field and drive a current through a circuit. This process is known as electromagnetic induction. Moving a magnet through a coil of wire or changing the current in a nearby coil can generate an electric current without a battery being directly connected. Electric generators use this principle to convert mechanical motion into electrical energy. Power stations rotate magnets or coils, creating changing magnetic fields that drive currents through wires. Transformers also rely on electromagnetic induction to change voltages within electrical systems. During the 19th century, James Clerk Maxwell brought these discoveries together into a unified mathematical theory. Maxwell's equations describe how electric charges create electric fields, how electric currents and changing electric fields produce magnetic fields, and how changing magnetic fields generate electric fields. The most remarkable result appeared when Maxwell studied how these fields could behave in otherwise empty space. A changing electric field could create a changing magnetic field, and that changing magnetic field could create another changing electric field. The disturbance could sustain itself and travel outward as a wave. Maxwell calculated the speed of these electromagnetic waves and found that it matched the known speed of light. Light was therefore revealed as electromagnetic radiation. Visible light is only a narrow region of the full electromagnetic spectrum. The spectrum also includes radio waves, microwaves, infrared radiation, ultraviolet radiation, X-rays, and gamma rays. These are not fundamentally different substances. They are forms of electromagnetic radiation, distinguished mainly by their frequency, wavelength, and energy. Radio waves have relatively low frequencies and long wavelengths. Gamma rays have extremely high frequencies and short wavelengths. Visible light lies between infrared and ultraviolet radiation, occupying only the small range that human eyes happen to detect. Quantum physics adds another layer to this description. The electromagnetic field exchanges energy in discrete units called photons. A photon is a quantum excitation of the electromagnetic field. It carries energy and momentum, but it has no rest mass. The energy of a photon depends on its frequency. This can be stated as photon energy equals Planck's constant multiplied by frequency. Higher frequency photons carry more energy. A gamma-ray photon therefore carries far more energy than a radio photon, even though both are excitations of the same electromagnetic field. Light becomes visible to us only because it interacts with matter. Electromagnetic radiation affects charged particles, especially electrons within atoms and molecules. Depending on the structure of the material and the energy of the incoming photons, light may be absorbed, emitted, reflected, refracted, transmitted, or scattered. Absorption occurs when matter takes in electromagnetic energy. An electron may move to a higher allowed energy state, or the energy may become molecular vibration, rotation, or disordered thermal motion. Emission occurs when matter releases electromagnetic energy. An excited atom can move into a lower energy state and emit a photon whose energy matches the difference between the two states. Reflection happens when electromagnetic radiation interacts with charges near a surface and is redirected. Refraction occurs when light changes direction as it enters a material in which its propagation is altered by repeated interactions with matter. Scattering redirects light in many possible directions. The blue colour of the daytime sky, for example, results largely from shorter visible wavelengths being scattered more strongly by molecules in Earth's atmosphere. Colour is not a coating painted onto atoms. It arises from the way a material interacts with different wavelengths of light, and from the way the eyes and brain process the radiation that reaches them. A red object under white light appears red because its material reflects or scatters more light from the red part of the visible spectrum while absorbing much of the rest. Change the illumination, and the appearance may change as well. A red surface placed under purely blue light may appear extremely dark because there is little red light available to reflect. Metals are often reflective because their mobile electrons respond strongly to incoming electromagnetic waves. The collective movement of these electrons produces radiation that travels back away from the surface, creating a reflected wave. Transparent materials allow certain wavelengths to pass because those photons do not match available transitions that would strongly absorb them. The electromagnetic wave still interacts with the material, which affects its speed and direction, but much of the light can continue through. Glass is transparent to much of visible light, but absorbs other parts of the spectrum more strongly. A material can therefore be transparent to one range of radiation and opaque to another. Human vision reveals only a small part of that selective behaviour. Atoms and molecules also produce characteristic spectra. Because their energy states are quantized, they absorb and emit only particular photon energies. When the resulting light is separated by wavelength, it forms distinctive lines or bands. These spectra act as physical fingerprints. Scientists can identify elements in distant stars by examining their light, determine the composition of gases, measure temperatures, and study molecular structures without directly collecting the material. Magnetism inside matter also depends on quantum behaviour. Electrons possess an intrinsic property called spin, which gives them a magnetic moment. Their orbital quantum states can contribute additional magnetic effects. In many materials, these microscopic magnetic moments point in different directions and largely cancel. In others, quantum exchange interactions favour aligned arrangements. Ferromagnetic materials, including iron, cobalt, and nickel, can form regions called magnetic domains. Within a domain, many atomic magnetic moments align in a common direction. In an unmagnetized piece of iron, the domains may point in different directions, producing little net magnetism. An external magnetic field can cause domains to grow or reorient. If enough alignment remains after the field is removed, the material becomes a permanent magnet. Paramagnetic materials contain magnetic moments that tend to align weakly with an applied field. Thermal motion disrupts much of this alignment, so the effect usually disappears when the external field is removed. Diamagnetic materials develop a weak magnetic response opposing an applied field. This behavior arises from changes in electron motion and occurs, at some level, in all matter. In most materials, it is masked by stronger magnetic effects. The magnetic character of a substance therefore depends not only on whether electrons are present, because electrons are present in all ordinary atoms. It depends on electron configurations, quantum states, interactions, temperature, crystal structure, and collective organization. Electromagnetism reaches through almost every familiar property of matter. It binds electrons to nuclei, holds atoms together in molecules, creates chemical reactions, produces the resistance felt as solidity, contributes to friction, controls electricity, generates magnetism, and determines how matter interacts with light. It also supports biological signaling. Nerve impulses depend on electrically charged ions moving across cell membranes. Molecules recognize and bind to one another through electromagnetic interactions. Vision begins when photons alter light-sensitive molecules inside the eye. What appears as a collection of separate effects is therefore one interconnected physical story. Color, current, magnetic attraction, chemical bonding, and the light crossing a room all arise through the behavior of charged particles and the electromagnetic field that extends between them. At the center of every atom lies an extraordinarily compact nucleus. It contains protons and neutrons, together known as nucleons, and it holds nearly all of the atom's mass. The surrounding electrons determine much of the atom's chemical behavior, but they contribute only a tiny fraction of its total mass. The difference in scale is remarkable. A typical atom is around 1/10 billionth of a meter across, while its nucleus is tens of thousands of times smaller. If an atom were expanded to the size of a large stadium, the nucleus would occupy only a tiny region near the center. Yet almost all the mass of the entire atom would be concentrated there. This immediately creates a puzzle. Every proton carries positive electric charge, and like charges repel through the electromagnetic force. A nucleus containing several protons should therefore experience intense internal repulsion. The more protons it contains, the stronger this competition becomes. Something else must bind the nucleus together. That binding arises from the strong nuclear interaction. At its deepest level, the strong interaction acts between quarks through particles called gluons. Protons and neutrons are themselves composite objects made from quarks and gluons. The force holding protons and neutrons together inside a nucleus is a residual effect of this more fundamental interaction, rather as a weak influence may remain outside an otherwise neutral object. The residual strong force is extremely powerful at the tiny distances found within nuclei, but it acts over only a very short range. It can attract neighbouring protons and neutrons strongly enough to overcome electrical repulsion when they're close together. Beyond a few millionths of a billionth of a meter, however, its influence falls away rapidly. Neutrons help nuclear stability because they contribute to the attractive strong interaction without adding electrical repulsion. Even so, not every mixture of protons and neutrons is stable. The balance depends on nuclear size, the proportion of neutrons to protons, quantum shell structure, and the energy of the complete nucleus. A bound nucleus has less mass than its separated protons and neutrons would have if measured individually and added together. This difference is called the mass defect. The missing mass has not vanished. It corresponds to the energy released when the nucleus formed. Albert Einstein's special theory of relativity connects mass and energy through the relationship energy equals mass multiplied by the speed of light multiplied by the speed of light. Because the speed of light is enormous, even a very small loss of mass corresponds to a substantial amount of energy. The energy required to break a nucleus apart into separate nucleons is called its nuclear binding energy. Atoms of the same chemical element always contain the same number of protons, but they may contain different numbers of neutrons. These versions are called isotopes. Carbon-12 and carbon-14 both contain 6 protons, so both are carbon. Carbon-12 contains 6 neutrons, while carbon-14 contains 8. Some isotopes are stable, others are unstable and transform through radioactive decay. Radioactivity was first discovered by Henri Becquerel, while Marie Curie and Pierre Curie carried out pioneering investigations of radioactive materials. Ernest Rutherford and Frederick Soddy later helped show that radioactive decay could transform one element into another. In alpha decay, an unstable nucleus emits an alpha particle containing 2 protons and 2 neutrons. The original nucleus therefore loses 4 nucleons and becomes a different element. In beta decay, the weak nuclear interaction changes the identity of a nucleon. In one common form, a neutron changes into a proton while emitting an electron and an antineutrino. The number of nucleons remains the same, but the number of protons changes, again producing a different element. Gamma emission is different. The numbers of protons and neutrons remain unchanged. Instead, an excited nucleus releases excess energy as a high-energy photon called a gamma ray. Radioactive decay is probabilistic. It is impossible to predict the exact moment when one particular unstable nucleus will decay. For a large population, however, the behavior becomes highly predictable. The half-life is the time required for half the unstable nuclei in a sample to decay on average. It is not a hidden timer attached to each atom. After one half-life, roughly half remain. After another, roughly half of those remain, and the pattern continues statistically. Nuclear energy can also be released through fission and fusion. Nuclear fission occurs when a heavy nucleus splits into smaller nuclei, usually releasing neutrons and energy. Uranium and plutonium isotopes can support chain reactions, because emitted neutrons may trigger further fission events. Nuclear fusion works in the opposite direction. Light nuclei combine to form heavier ones. Under the right conditions, the resulting nucleus is more tightly bound, so part of the original mass becomes released energy. Fusion powers the sun. In its core, temperatures reach roughly 15 million degrees Celsius, and immense pressure keeps hydrogen nuclei densely packed. Through a sequence known as the proton-proton chain, hydrogen is gradually converted into helium. A small fraction of the original mass becomes energy, which eventually leaves the sun as light, heat, and other forms of radiation. The International Atomic Energy Agency supports international cooperation in the peaceful use of nuclear science and technology. It also monitors nuclear materials, promotes safety standards, and carries out inspections intended to reduce the spread of nuclear weapons. Nuclear structure connects the smallest regions of matter with some of the largest events in the universe. Fusion inside stars builds elements up to iron and nearby nuclei. Supernova explosions and neutron star mergers create conditions in which many heavier elements can form. Gold, platinum, uranium, and other heavy nuclei were produced through extreme cosmic events long before Earth existed. Radioactive isotopes allow scientists to date rocks, archaeological materials, and events in Earth's history. Nuclear processes are used in medical imaging, cancer treatment, scientific research, and electricity generation. The nucleus is therefore not merely a dense packet hidden inside the atom. It is a quantum system shaped by competing forces, binding energy, probability, and nuclear structure. Within its tiny volume lie the processes that power stars, transform elements, release radioactivity, and help build the chemical contents of planets and living bodies. For a time, the proton and neutron seemed to be the final heavy building blocks of ordinary matter. Electrons surrounded the atomic nucleus, while protons and neutrons formed its compact interior. Yet as experiments reached higher energies and shorter distances, these nuclear particles began to reveal structures of their own. The basic method was scattering. Physicists directed fast-moving particles toward a target and studied how they emerged after the collision. This is similar in principle to learning the shape of a hidden object by throwing small projectiles at it and recording where they bounce, although particle experiments are rather more precise and generally involve fewer damaged windows. Low-energy probes may respond only to the overall size and charge of a target. More energetic probes have shorter associated wavelengths and can reveal finer details. As accelerator technology improved, experiments showed that protons and neutrons were not smooth, indivisible particles. Their internal electric and magnetic behavior suggested that charge and momentum were distributed among smaller constituents. During the 1960s, Murray Gell-Mann and George Zweig independently proposed that strongly interacting particles were built from more fundamental objects. Gell-Mann called them quarks, while Zweig initially used the name aces. The quark model brought order to the rapidly expanding collection of particles being discovered in cosmic rays and particle accelerators. 6 types of quark are now known. They are called up, down, strange, charm, top, and bottom. Physicists refer to these types as flavors, a name that does not imply any culinary property. Ordinary stable matter depends almost entirely on the up and down quarks. The heavier flavors are produced in energetic processes and decay into lighter particles. A proton contains 2 up valence quarks and 1 down valence quark, because an up quark carries positive electric charge equal to 2/3 of the proton's charge, while a down quark carries negative charge equal to 1/3 of the proton's charge. The total charge of this combination is +1. A neutron contains 1 up valence quark and 2 down valence quarks. Their charges add to 0, giving the neutron no net electric charge. This neat accounting explains the familiar charges of protons and neutrons, but it can also create an oversimplified picture. A proton is not merely a bag containing 3 small balls. The 3 valence quarks determine its persistent quantum identity, but its interior also contains a dense and continually changing system of gluons, along with temporary quark and antiquark contributions. These additional components arise through the behavior of quantum fields and contribute to the proton's momentum, spin, and energy. The theory describing quarks, gluons, and the strong interaction is called quantum chromodynamics. It is part of the standard model of particle physics and is one of the most successful quantum field theories ever developed. Quarks carry a property known as color charge. This has nothing to do with visual color. The labels red, green, and blue are simply names for 3 possible forms of strong interaction charge. Antiquarks carry corresponding anticolors. Observable composite particles are color neutral. In a proton or neutron, the 3 valence quarks combine so that their color charges form an overall neutral state. A quark and an antiquark can also combine their color and anticolor into a neutral particle known as a meson. The strong interaction is transmitted through gluons. Gluons are quantum excitations of the gluon fields, rather as photons are excitations of the electromagnetic field. However, there is an important difference. Photons do not carry electric charge, so they do not interact directly with one another under ordinary conditions. Gluons carry color charge. They therefore interact with quarks and also with other gluons. This self-interaction makes quantum chromodynamics especially rich and mathematically difficult. One of its most striking consequences is confinement. Quarks are not observed as isolated particles under ordinary conditions. Attempting to pull 2 quarks apart does not cause the strong interaction to fade away in the same simple manner as the electric force between distant charges. Instead, the energy stored in the gluon field between the quarks increases. If enough energy is supplied, it becomes favourable for new quark and antiquark pairs to form. The result is not one free quark, but new colour neutral particles. High-energy collisions therefore produce sprays of composite particles called jets, rather than isolated quarks. At very short distances, the strong interaction behaves in the opposite way. Quarks interact more weakly when they are extremely close together or involved in very high energy processes. This property is called asymptotic freedom. David Gross, Frank Wilczek, and David Pulitzer discovered the theoretical basis of asymptotic freedom during the early 1970s. Their work showed that quantum chromodynamics could explain why quarks sometimes appeared almost free inside rapidly moving protons, while remaining permanently confined at larger distances. Critical experimental evidence came from deep inelastic scattering at the Stanford Linear Accelerator Center. Beginning during the late 1960s, energetic electrons were fired into protons and neutrons. The electrons scattered as though they were striking compact point-like constituents inside the nucleons. The results resembled an earlier scientific turning point. Ernest Rutherford had used alpha particle scattering to reveal the atomic nucleus. Deep inelastic scattering now used electrons to reveal structure within the proton itself. The point-like constituents observed in these experiments were initially called partons, a term introduced by Richard Feynman. As the quark model and quantum chromodynamics developed, the partons were identified mainly with quarks and gluons. These experiments also revealed that the proton's momentum is shared dynamically among its constituents. The valence quarks carry only part of the total. Gluons and fluctuating quark and antiquark contributions account for much of the rest, especially when the proton is examined at extremely high energies. This internal activity is central to one of the most surprising facts about ordinary matter. The intrinsic masses of the up and down quarks contribute only a small fraction of the mass of a proton or neutron. Most nucleon mass arises from the energy contained in the quark and gluon fields, including the motion of quarks, the energy stored in gluon interactions, and the complex quantum dynamics required by confinement. Through Albert Einstein's equivalence of mass and energy, this internal energy appears as mass. The relation can be stated as energy equals mass multiplied by the speed of light multiplied by the speed of light. A proton has a rest energy of roughly 938 million electron volts. The combined intrinsic masses of its three valence quarks account for only a few % of that value. The great majority emerges from quantum chromodynamics. This means that most of the mass in ordinary visible objects does not come directly from the Higgs-generated masses of their elementary quarks. The Higgs field helps give the quarks their intrinsic masses, but the bulk of the proton and neutron mass comes from strong interaction energy. A stone, a glass of water, and a human body therefore owe most of their mass to the energetic behavior of confined quark and gluon fields. Matter feels heavy, partly because the interior of every proton and neutron is an intensely active quantum system. Quantum chromodynamics is tested through experiments at laboratories around the world. The European Organisation for Nuclear Research, located near Geneva, operates the Large Hadron Collider, the most powerful particle accelerator yet constructed. The collider accelerates protons to extremely high energies and brings them into collision inside detectors operated by collaborations, including ATLAS, CMES, ALICE, and LHCb. Because protons are composite, each collision is really an interaction among quarks and gluons carrying fractions of the incoming proton energy. By analysing the resulting particle jets and decay patterns, researchers test quantum chromodynamics, measure the structure of protons, and search for signs of unknown physics. Heavy ion collisions also create extremely hot matter in which quarks and gluons briefly behave as a quark-gluon plasma rather than remaining confined inside individual protons and neutrons. The proton, once treated as a simple positive particle, is therefore a restless quantum world. Its valence quarks establish its identity, gluons bind and interact throughout its interior, and fluctuating fields continually reshape the distribution of energy and momentum. At the deepest experimentally confirmed level, most familiar mass is not a pile of tiny heavy objects. It is energy held within the structure and motion of quantum fields. The weight of ordinary matter begins inside protons and neutrons, where quarks remain confined and gluons quietly carry much of the substance of the visible world. The standard model of particle physics is the most successful framework currently used to describe the known elementary particles and 3 of the 4 fundamental interactions. It includes electromagnetism, the strong interaction, and the weak interaction. Gravity is not part of the standard model and is instead described separately by Albert Einstein's general theory of relativity. The matter particles of the standard model are divided into 2 main groups, quarks and leptons. Both belong to the broader quantum category known as fermions. Fermions possess half-integer spin and obey the Pauli exclusion principle, which prevents identical fermions from occupying the same complete quantum state. There are 6 quark flavors: up, down, strange, charm, top, and bottom. Quarks combine to form composite particles such as protons and neutrons. Ordinary stable matter depends mainly on up quarks, down quarks, and electrons. The leptons also come in 6 forms. 3 carry electric charge: the electron, the muon, and the tau particle. Each has an associated electrically neutral neutrino: the electron neutrino, the muon neutrino, and the tau neutrino. Muons and tau particles resemble heavier versions of the electron, but they are unstable and decay rapidly into lighter particles. Electrons are stable and form the outer structures of atoms. Neutrinos interact only weakly with ordinary matter, allowing vast numbers of them to pass through planets, bodies, and detectors without leaving any trace. Every matter particle also has a corresponding antiparticle. An antiparticle has the same mass as its partner, but opposite electric charge and reversed values for certain other quantum properties. Paul Dirac predicted antimatter through his relativistic quantum theory of the electron. In 1932, Carl Anderson discovered the positron, the electron's positively charged antiparticle, in cosmic ray tracks. When a particle meets its antiparticle, they may annihilate. Their mass and energy are converted into other particle excitations, often including photons. The reverse process, known as pair production, can occur when sufficient energy creates a particle and its antiparticle together. Neither annihilation nor pair production violates conservation of energy. Matter does not simply disappear, and particles do not appear without a physical source. Energy, momentum, electric charge, angular momentum, and other conserved quantities must balance before and after the interaction. The forces of the standard model are associated with particles called gauge bosons. The photon carries the electromagnetic interaction between electrically charged particles. Gluons carry the strong interaction between quarks. The weak interaction is carried by 2 electrically charged weak bosons and 1 neutral weak boson. The weak interaction is responsible for several forms of radioactive beta decay. It can change one type of quark into another, allowing a neutron to transform into a proton, or a proton to transform into a neutron under suitable conditions. This interaction is also essential inside stars. The first stage of the proton-proton chain in the Sun requires 1 proton to become a neutron through a weak interaction process. Without the weak interaction, the Sun could not fuse hydrogen into helium in its familiar way. Neutrinos interact through the weak force and gravity, although their gravitational effects are usually extremely small. They were once thought to have no mass, but observations of neutrino oscillation show that this could not be correct. Neutrino oscillation means that a neutrino produced in one flavor state can later be detected as another. Experiments at Super Kamiokande in Japan showed that neutrinos created in Earth's atmosphere changed flavor while traveling. The Sudbury Neutrino Observatory in Canada demonstrated that neutrinos arriving from the Sun were also changing among flavor states. Oscillation requires differences among neutrino masses, showing that at least some neutrinos possess small but non-zero mass. The standard model in its simplest original form treated neutrinos as massless, so this discovery revealed that the theory requires extension. particles are classified using measurable properties including mass, electric charge, spin, lifetime, and the interactions in which they participate. Some are stable, while others survive for only tiny fractions of a second. Short-lived particles can still be studied using particle accelerators. In high-energy collisions, energy is concentrated strongly enough to create massive particle excitations. These particles then decay, leaving tracks, energy deposits, or other signals inside detectors. Researchers reconstruct the original event from these decay products. The process resembles identifying a brief and invisible event from the fragments it leaves behind, although the fragments may themselves decay before making matters helpfully straightforward. The Standard Model has passed an enormous range of experimental tests. Its predictions agree with measurements to extraordinary precision, and every elementary particle it requires has been observed, including the Higgs boson. Yet the framework is incomplete. It does not contain a quantum theory of gravity. It does not identify dark matter, fully explain neutrino masses, or account for the overwhelming dominance of matter over antimatter in the observable universe. It also contains several particle masses and interaction strengths that must be measured rather than derived from deeper principles. Despite its large particle inventory, ordinary material relies on only a small part of the complete model. Stable atoms are built primarily from electrons, up quarks and down quarks. Photons mediate electromagnetic interactions, while gluons bind quarks inside protons and neutrons. The heavier quarks and leptons appear naturally in energetic environments but decay rapidly. Everyday matter is therefore not made from every known elementary particle in equal measure. It is built from a remarkably limited and stable selection, supported by fields and interactions extending throughout space. The Standard Model turns the foundations of matter into an organized quantum family. Some particles form the lasting substance of planets and bodies. Others appear only briefly in cosmic rays, radioactive processes, stars, and accelerator collisions. Together, they provide the most complete experimentally tested inventory of the microscopic world that physics has yet produced. A field is a way of assigning a physical quantity to every location in space and time. A weather map can show a temperature field, with a different temperature at each place. A gravitational field describes how an object would accelerate at different locations. Electric and magnetic fields describe how charged particles would respond throughout the surrounding region. In classical physics, fields were already more than convenient diagrams. Michael Faraday treated electric and magnetic fields as real features of nature, while James Clerk Maxwell showed that changing electric and magnetic fields could travel through space as electromagnetic waves. Modern physics goes further. Quantum field theory combines quantum mechanics with Albert Einstein's special theory of relativity. In this framework, fields are treated as fundamental quantum entities, while particles appear as discrete excitations of those fields. An electron is an excitation of the electron field. A photon is an excitation of the electromagnetic field. Quarks are excitations of quark fields, and gluons are excitations of gluon fields. What we call a particle is therefore not necessarily a tiny independent object added to the universe from outside. It is a particular quantist state of a field already present throughout space. This does not mean that a quantum field is an ordinary fluid filling the universe. It has no simple texture, color, or mechanical substance. A field is described mathematically through values, quantum states, symmetries, and interactions. It can exist in its lowest energy state, even where no particle is detected. Quantum field theory also allows particles to be created and destroyed. This is essential because high-energy collisions routinely produce new particles, while unstable particles decay into others. The older assumption that the number of particles must always remain fixed cannot describe such events. What remains conserved are quantities such as energy, momentum, electric charge, and angular momentum. A photon can produce a particle and antiparticle pair if enough energy is available and all conservation laws are satisfied. A particle and antiparticle can annihilate into other field excitations. The ingredients change form, but the physical accounting remains intact. One of the great achievements of quantum field theory is quantum electrodynamics, the theory describing interactions between charged particles and the electromagnetic field. Richard Feynman, Julian Schwinger, Shinichiro Tominaga, and Freeman Dyson made central contributions to its development during the 20th century. Quantum electrodynamics predicts quantities such as the magnetic properties of the electron with extraordinary accuracy. In some cases, theory and experiment agree to more than 10 decimal places. Few descriptions in science have ever survived such demanding comparison. Calculations in quantum field theory often use diagrams and mathematical terms involving virtual particles. These are useful features of perturbation theory, a method for approximating interactions through a series of increasingly detailed corrections. Virtual particles should not be pictured too literally. They are not ordinary temporary objects that pop into existence, borrow energy from nowhere, and then vanish before nature notices. They are internal elements of a calculation and do not satisfy the same measurable relationships as real particles detected in experiments. The lowest energy state of quantum fields is called the quantum vacuum. It is not absolute nothingness. The fields remain present, and their quantum state still possesses structure. Quantum systems cannot generally be assigned perfectly fixed values for all relevant quantities at once. As a result, even the vacuum is associated with fluctuations in zero-point energy. These ideas must be handled carefully. They do not mean that empty space contains an unlimited reservoir of easily extractable energy. One experimentally grounded effect associated with quantum fields and boundaries is the Casimir effect. Two closely spaced conducting surfaces alter the allowed electromagnetic field states between and outside them. Under suitable conditions, this produces a measurable force. The Casimir effect is real, but it is better understood through changes in field energy and quantum correlations than through a simplistic image of particles continually appearing from nothing and pushing on the plates. Interactions between particles arise because their corresponding fields are coupled. The electron field couples to the electromagnetic field because electrons carry electric charge. Quark fields couple to gluon fields because quarks carry color charge. The possible couplings are restricted by symmetries. A symmetry means that certain transformations leave the underlying physical description unchanged. These principles are not merely decorative mathematical preferences. They determine which interactions are allowed and help enforce conservation laws. Gauge symmetry is especially important within the Standard Model. At a technical level, it concerns particular transformations in the mathematical description of fields. Physically, it organizes the structure of the electromagnetic weak and strong interactions and determines the gauge bosons associated with them. The word symmetry can make the theory sound visually simple, but the mathematics is demanding. Its importance lies in the way it limits the possible laws. Instead of allowing fields to interact arbitrarily, gauge symmetry imposes a disciplined structure that experiments have repeatedly confirmed. Quantum field theory is therefore the most accurate known language for describing elementary particles and their interactions. It explains scattering experiments, radioactive processes, antimatter, particle creation, atomic corrections, and the behavior of high-energy collisions. Yet its meaning remains conceptually subtle. Physicists can calculate what experiments will record with astonishing precision, while still debating the deepest interpretation of quantum states, fields, particles, and measurement. Even so, the practical picture is powerful. A solid object can be understood as a stable, organized pattern within interacting quantum fields. Electrons occupy persistent states around nuclei. Quarks and gluons form protons and neutrons. Electromagnetic fields bind atoms into molecules, while quantum rules prevent matter from collapsing into simpler arrangements. The objects around us are not separate from the fields beneath them. They are long-lasting structures made possible by those fields. A table, a stone, or a human body is a highly organized excitation pattern that remains stable because the underlying fields interact in precise and repeatable ways. Matter may therefore be less like a collection of independent little objects and more like a set of enduring patterns in fields extending through space. The particle remains useful and measurable, but the field provides the deeper framework from which the particle emerges. Asking where mass comes from sounds like a single question, but physics gives several different answers. The mass of an elementary particle is not explained in exactly the same way as the mass of a proton. The mass of an atomic nucleus includes binding energy. The mass of an ordinary object includes the rest energies and interactions of all its parts. One word is doing several related jobs. The Higgs field provides one important part of the answer. It is a quantum field with a non-zero value throughout the vacuum. In the electroweak theory, this background field allows certain elementary particles to possess rest mass while preserving the mathematical consistency of the underlying laws. The mechanism was developed during the 1960s through work by several physicists, including Peter Higgs, François Englert, Robert Brute, Gerald Guralnick, Carl Hagen, and Tom Kibble. Their proposals described how particles could acquire mass through interaction with a field-filling space, rather than having mass inserted into the theory by hand in a way that broke its essential symmetries. The central idea involves spontaneous symmetry breaking. The phrase sounds dramatic, but the principle can be described quite gently. The underlying laws may possess a symmetry, while the lowest energy state of the system does not display that symmetry in the same obvious way. A simple comparison is a perfectly balanced object sitting at the top of a rounded hill. The situation is symmetric because there is no preferred direction for it to fall. Once it rolls down and settles at one particular point, the laws remain symmetric, but the chosen resting state no longer looks the same in every direction. The Higgs field behaves in a more abstract quantum way, but the broad idea is similar. Its lowest energy state has a non-zero value. This changes how other fields behave throughout space. Before electroweak symmetry breaking, the electromagnetic and weak interactions are described as parts of one unified structure. Through interaction with the Higgs field, the charged weak bosons and the neutral weak boson acquire large rest masses. The photon does not acquire mass and remains massless. This difference has visible consequences. The massless photon allows the electromagnetic interaction to act over enormous distances. The weak bosons are very massive, so the weak interaction is effective only across extremely short subatomic ranges. Elementary matter particles also receive mass through their couplings to the Higgs field. Electrons, quarks, and other fermions interact with the field with different strengths. A stronger coupling corresponds to a greater elementary rest mass. The electron couples weakly and is comparatively light. The top quark couples much more strongly and is extraordinarily heavy for an elementary particle. The standard model accurately describes this relationship once the coupling strengths are known, although it does not yet explain why the particles possess those particular values. The Higgs field is sometimes compared with a thick substance that slows some particles more than others. This can be a useful first image, but it becomes misleading very quickly. The field does not act like honey, syrup, or any other viscous medium. A particle moving through the Higgs field does not continually lose energy through drag. Empty space does not resist uniform motion merely because the Higgs field is present. Mass concerns how a particle's energy and momentum are related and how strongly it resists acceleration. It is not produced by microscopic rubbing against a cosmic substance. Otherwise, objects moving through space would gradually slow down, which is not what the Higgs mechanism predicts. The Higgs boson is not the Higgs field itself. It is a detectable quantum excitation of that field, rather as a photon is an excitation of the electromagnetic field. Finding the boson provided strong evidence that the field and mechanism were physically real. In 2012, the Atlas and CMS collaborations at the Large Hadron Collider announced the discovery of a new particle consistent with the Higgs boson. The collider is operated by the European Organisation for Nuclear Research near Geneva. The detected particle had a mass of approximately 125 billion electron volts when expressed in the energy units commonly used in particle physics. Later measurements of its spin, decay patterns, and interactions continue to support its identification as the Higgs boson predicted by the Standard Model. Yet the Higgs field does not account for most of the mass in ordinary matter in the way people sometimes assume. It gives elementary quarks their intrinsic masses, but those quark masses make up only a small fraction of the mass of a proton or neutron. Most of the mass of protons and neutrons comes from the energy of the strong interaction. Quarks and gluons move, interact, and remain confined inside each nucleon. The energy stored in those quantum fields contributes to the nucleon's mass through Albert Einstein's relation energy equals mass multiplied by the speed of light multiplied by the speed of light. An ordinary atom contains a nucleus made from protons and neutrons surrounded by electrons. Because the nucleus carries nearly all the atom's mass, most of the mass of everyday matter ultimately arises from quantum chromodynamics rather than directly from the Higgs-generated masses of elementary quarks. Nuclear binding also changes mass. A bound nucleus usually has slightly less mass than the combined masses of its separated protons and neutrons. The difference corresponds to the energy released when the nucleus formed. Chemical binding contributes smaller changes of the same general kind. The mass of a complete object therefore includes all the energy stored within it. Heating an object technically increases its mass by an extremely small amount because its internal energy has risen. Compressing a spring also adds a tiny amount of mass through the energy stored in the deformation. These effects are real, although far too small to notice on an ordinary household scale. Mass should also be distinguished from weight. Mass measures a system's inertia and contributes to its rest energy. Weight is a force produced by gravity in a particular environment. An astronaut carries essentially the same mass on Earth, on the Moon, or while orbiting in apparent weightlessness. The astronaut's weight changes because the local gravitational situation changes. The amount of matter and internal energy does not simply vanish when the bathroom scales become less judgmental. The Higgs mechanism is therefore essential, but it is one layer in a larger explanation. It accounts for the rest masses of certain elementary particles and for the large masses of the weak bosons. Strong interaction energy creates most of the mass of protons and neutrons. Binding energy modifies the mass of nuclei and molecules. The total energy of a composite system contributes to the mass of the whole. Matter possesses mass not through one universal microscopic trick, but through several connected mechanisms. The Higgs field supply is part of the foundation, while quantum fields, confinement, motion, and binding complete the weight of the world around us. Complex materials reveal one of the most important ideas in physics: emergence. Emergence occurs when many interacting components produce organized behavior that does not belong to any one component alone. The resulting properties are not illusions or convenient descriptions. They are real, measurable features of the larger system. Carbon provides a striking example. The same carbon atoms can form diamond, graphite, graphene, fullerenes, and many other structures. Their atomic ingredients are identical, yet their hardness, conductivity, transparency, and mechanical behavior can differ dramatically. In diamond, each carbon atom forms strong covalent bonds within a rigid three-dimensional network. Distorting this network requires many strong bonds to be disrupted, giving diamond its exceptional hardness. Graphite has a layered structure. Carbon atoms bond strongly within flat sheets, but the attraction between neighbouring sheets is much weaker. The layers can slide over one another, making graphite soft enough to leave marks on paper. Delocalized electrons also move through the sheets, allowing graphite to conduct electricity. Graphene is essentially a single carbon layer arranged in a hexagonal pattern. It is extremely strong for its thickness, flexible, nearly transparent, and an excellent conductor. Fullerenes curve carbon networks into cages and tubes, producing another family of properties from the same elemental ingredient. Material behavior also depends on imperfections. Crystal structure, impurities, grain boundaries, and processing history can change how metals, ceramics, semiconductors, and other solids respond to force, heat, electricity, or light. Crystals contain line defects called dislocations. Their movement allows layers of atoms to shift gradually, so a material can deform without every bond breaking simultaneously. Preventing dislocations from moving easily can strengthen a metal. This can be achieved through added impurities, smaller crystal grains, or carefully controlled heat treatment. Polymers create complexity in a different way. They consist of long molecular chains whose properties depend on chemical composition, length, branching, entanglement, and cross-linking. Flexible chains with limited cross-linking may form soft rubber, while more rigid or strongly connected structures can produce hard plastics. Composite materials combine different components so that their useful properties complement one another. Bone combines a flexible collagen framework with hard mineral crystals. Wood contains strong cellulose fibers within a surrounding biological matrix. Reinforced concrete combines concrete's resistance to compression with steel strength under tension. Carbon fiber materials place strong, lightweight fibers inside a binding resin. Collective behavior can become even stranger at low temperatures. In 1911, Heike Kamerlingh Onnes discovered that mercury lost its ordinary electrical resistance when cooled sufficiently. This phenomenon became known as superconductivity. In conventional superconductors, the Bardeen-Cooper-Schrieffer theory developed by John Bardeen, Leon Cooper, and John Robert Schrieffer explains how electrons form correlated pairs. These Cooper pairs enter a coherent quantum state that can move through this material without ordinary resistance. Superfluidity provides another example of quantum behavior extending across a large system. A superfluid can flow with extremely low viscosity and display behavior impossible for a classical liquid. Bose-Einstein condensation arises when certain particles are cooled until many occupy the same quantum state. Satyendranath Bose and Albert Einstein developed the underlying statistical theory during the 1920s. Decades later, groups led by Eric Cornell, Carl Wieman, and Wolfgang Ketterle created dilute atomic Bose-Einstein condensates in laboratories. In these systems, quantum coherence is no longer confined to one microscopic particle. Large numbers of particles behave collectively through a shared state. Topological materials add another layer of organization. Their electronic behavior can depend on global features of quantum states, rather than only on local atomic bonding. Some possess protected conducting states at their surfaces or edges that remain surprisingly resistant to certain imperfections. Knowing the fundamental particles is therefore not enough to predict every useful property of matter. Electrons, quarks, and fields provide the ingredients, but arrangement, interaction, temperature, environment, and scale determine what those ingredients become. Materials science uses this principle deliberately. Batteries depend on controlling how ions and electrons move through carefully chosen structures. Computer chips rely on precisely patterned semiconductors. Solar cells guide electrons through engineered energy bands. Medical implants require combinations of strength, stability, and biological compatibility. Aircraft components balance low mass with resistance to stress and heat. Communication devices depend on materials designed to manipulate electric currents and electromagnetic waves. The complexity of matter does not require an endless list of fundamental ingredients. It arises because a limited set of particles and forces can organize itself in an immense number of ways. The deepest laws provide the possibilities, but structure decides which possibilities become real. Ordinary matter occupies a modest place in the universe, but it is the form of matter we know most intimately. Atoms make up stars, planets, moons, gas clouds, cosmic dust, oceans, living organisms, and nearly everything seen directly through emitted, reflected, or absorbed electromagnetic radiation. The earliest atomic nuclei formed within the first few minutes after the beginning of the hot early universe. During Big Bang nucleosynthesis, temperatures and densities allowed protons and neutrons to combine into light nuclei. Most of the resulting ordinary matter remained hydrogen, with a substantial amount of helium and small traces of lithium and other light nuclei. The heavier elements required stars. Inside stellar cores, nuclear fusion combines lighter nuclei into heavier ones. Hydrogen becomes helium, while sufficiently massive and evolved stars can build carbon, oxygen, neon, silicon, and elements around iron. Some of these materials are carried into space by stellar winds. Others are expelled during supernova explosions, or created and dispersed during neutron star mergers. The scientific account of stellar element formation was transformed by Margaret Burbidge, Geoffrey Burbidge, William Fowler, and Fred Hoyle. Their influential work explained how many chemical elements could be assembled through nuclear reactions inside stars. Cecilia Payne-Gaposchkin had earlier demonstrated that stars are composed mainly of hydrogen and helium, overturning the assumption that they closely resembled Earth in composition. The carbon in living tissue, the oxygen carried through the blood, the calcium in bones, and the iron within hemoglobin were not present in the earliest universe in their current forms. They were assembled through generations of stars scattered into space, incorporated into new clouds, and eventually gathered into planets and living systems. Yet ordinary atomic matter is not the dominant component of the modern cosmological picture. Cosmologists distinguish baryonic matter, which includes protons, neutrons, atoms, stars, gas, and living bodies, from dark matter, whose identity remains unknown. Dark matter does not appear to absorb, emit, or reflect light in the familiar way. Its presence is inferred from gravity. During the 1930s, Fritz Zwicky found that galaxies within the Coma cluster were moving as though far more mass were present than could be seen. Decades later, Vera Rubin and Kent Ford measured the rotation of spiral galaxies. Stars far from galactic centers were moving faster than the visible distribution of matter appeared able to support. These rotation curves suggested that galaxies are surrounded by extended regions of unseen mass. Further evidence comes from gravitational lensing, galaxy cluster dynamics, the cosmic microwave background measured by missions including Planck, and the growth of galaxies across cosmic history. Together, these observations indicate that dark matter plays a central role in shaping the large-scale structure of the universe. Dark energy presents a different mystery. It is the name given to whatever is driving the observed acceleration of cosmic expansion. In current cosmological models, ordinary matter contributes only a minority of the universe's total energy density, while dark matter and dark energy account for most of the remainder. Antimatter adds another unfinished problem. Antiparticles are real and are routinely produced in radioactive processes, cosmic ray collisions, medical technologies, and particle accelerators. When matter and antimatter meet, they can annihilate into other forms of energy while obeying conservation laws. The observable universe, however, contains far more matter than antimatter. The process that produced this imbalance is called baryogenesis. In 1967, Andrei Sakharov described broad conditions that a successful explanation would require, including processes that do not treat matter and antimatter in exactly the same way, and conditions far from thermal equilibrium. The Standard Model contains some relevant asymmetries, but they do not appear sufficient to explain the observed dominance of matter. Why anything made from atoms remains at all is therefore connected to physics that is still incompletely understood. gravity creates another boundary in present knowledge. Quantum field theory describes particles and three fundamental interactions with exceptional accuracy, while general relativity describes gravity and space-time. A complete experimentally confirmed theory of quantum gravity has not yet united them. Without that deeper framework, matter cannot be fully described under the most extreme conditions, including the central regions of black holes or the earliest accessible moments of cosmic history. Other questions remain open. The absolute masses of neutrinos and the mechanism producing them are not fully known. Dark matter has not been identified as a confirmed particle. The long-term stability of the Higgs vacuum remains connected to precise particle properties and physics at extremely high energies. Quark confinement is successfully described by quantum chromodynamics, but extracting exact predictions in the low-energy regime remains mathematically difficult. Physicists also do not know whether quarks, electrons, and the other known elementary particles are truly indivisible, or whether a deeper structure waits beyond current experimental reach. Matter is therefore not one simple substance. It is a hierarchy of quantum fields, elementary particles, fundamental interactions, composite nuclei, atoms, molecules, materials, and emergent structures. Each level follows from the one beneath it, yet introduces properties that become meaningful only when many parts interact. A familiar object is ordinary because it behaves reliably. It is profound because its atoms contain particles forged by ancient physical processes, while many of its elements were assembled inside long-dead stars. Stone, water, metal, skin, and air are stable arrangements of fields and particles shaped by laws operating from the interior of the proton to the scale of the observable universe. Matter surrounds us quietly, but its full explanation reaches through nearly every part of physics and into some of its deepest unanswered questions. Matter actually works through layers. Quantum fields produce elementary particles. Fundamental interactions organize those particles into nuclei and atoms. Chemical bonds build molecules, and statistical behavior turns enormous collections of them into familiar materials. The path from ancient elements and indivisible atoms led eventually to electrons, atomic nuclei, quantum states, quarks, gauge bosons, and the Higgs field. An ordinary object is therefore not simply a heap of tiny solid pieces. Its apparent solidity emerges largely from electromagnetic interaction, and the Pauli exclusion principle acting throughout an organized quantum system. A surprisingly small set of ingredients can create an immense variety of substances, because structure matters as much as composition. The Higgs field contributes to elementary particle masses, while most ordinary atomic mass arises from strong interaction energy inside protons and neutrons. Quantum fields provide the deepest successful description currently available, with particles appearing as quantized excitations of those fields. Air, water, skin, stone, metal, glass, and living tissue are all temporary but stable arrangements of ancient physical ingredients. Dark matter, matter, antimatter, asymmetry, quantum gravity, and possible structures beyond the standard model remain unresolved. Matter feels permanent only because its foundations organize themselves with extraordinary reliability, and while everything around you appears still and silent, its fields, electrons, nuclei, and thermal motions continue their intricate activity beneath the surface.